Well, well, I think we can continue now before it gets even later. Now we have this other session of our Journées Scientifiques that is titled Frontiers in Astrophysics, Astronomy and Quantum Computing, a very interesting topic. And the first presentation is a keynote by Professor Guillermo Cabrera. It takes time to read it's not so mini, your mini bio. He's associate professor at the Department of Computer Science of the University of Concepcion. His research interests include machine learning, computer vision, data science, astroinformatics, and bioinformatics. His work is focused in developing new algorithms for massive observational data from a wide variety of astronomical instruments such as ALMA, SDSS, HST, and LSST, among others. He's a founding member of the Astroinformatics Laboratory of the Center for Mathematical Modeling, and he's currently a member of the Millennium Institute of Astrophysics and the Millennium Nucleus on Young Exoplanets and Their Moon. He's the founder and director of the Data Science Unit at the University of Concepcion, where he applies state-of-the-art data science tools and to real-world problems in the industry and society. So please, let's welcome and thank Guillermo. All yours.
Thank you, Luis, and thanks to all of you for being here, especially after lunch. I guess you might be a little bit sleepy, hopefully not too much, so that we can have some fun today. This is the title of my presentation, Unleashing the Power of Transformers for the Analysis of Cosmic Streams. I have to be honest, this was written by ChatGPT. Okay, so whenever you read unleashing the power of something, it's usually ChatGPT behind it. Okay. Okay, does this work? Yeah. Okay, so I'm going to talk about cosmic streams. Basically, this is like how we're perceiving the light that's coming from the universe. And in order to talk about that, I'll start by talking about survey telescopes and brokers. And okay, so I'm not sure how many of you guys know about the Vera C. Rubin telescope. Can you raise your hands if you know about it? Okay, in case you don't know about it, this is one of the major telescopes nowadays. It's still not operating. We're expecting it to start operating next year, 2024. And we've been preparing for this for like 2 decades already, all right? So I'm not sure if you know about this, but when we build a telescope, it's like 10 years just to design it and then 10 more years to build it, okay? So when this starts operating, it's going to be like a 2 decades success, okay? So just so you know, the amount of data that this telescope is going to collect, it's around 15 terabytes of data per night. So that means that if we're not able to process those 15 terabytes of data tonight, then we're going to have a huge problem, because next night we're going to have another 15 terabytes of data, all right? And we've been preparing for this, as I said, for a lot of years. And what we expect to be able to discover is something like this. So for each visit, for each observation that the telescope takes, we're expecting to have around 7,000 variable stars, 3,000 solar system objects, and a lot of other things, okay? And this is per image, right? And you can see here that we're expecting to be able to detect around 37 billion objects in total during the 10 years that this is going to be running. And the way this is going to run is that approximately every 3 nights, you're going to have a picture of the whole sky, of the whole observable sky. So that means that we're going to have like a movie, like a film, that's going to be like a really large film that it will have like every 3 days the same object, okay? And why is this important? Well, because we're going to be able to do things that we were never able to do in the past at this scale. Okay, and for example, what we're going to do is we're going to be able to track asteroids, asteroids that potentially can hit the Earth. We're going to be able to see all the varying things in the sky that nowadays we can do it nowadays, but not at this scale. Okay, and the way we're going to do this is something like this. So we have an image here. For example, this is a supernova, which is basically a star that exploded. And we take the image tonight, and you can see that there's like a small point there. And we compare it against a reference image from the past, where the explosion was not there. And then we subtract them, and you can see that there is something there, like a point, right? And we're expecting to receive about 10 million of those points per night. Okay, so that's kind of a lot, if you think about it. And we need to be able to sort them out, right? A lot of them are going to be just like garbage. We're not going to care about them. But a lot of them, or some of them, may be really important, such as an asteroid that can hit the Earth. That's like just to catch your attention, right? Okay, so for the past 20 decades, this has been like a ghost that's been haunting us. Like, how are we going to deal with all this, right? And now this is coming a reality, and now we have an idea on how we're going to work with this. So the future of time domain ecosystem is going to be something like this. We're going to have the survey telescopes, and it's not just the LSST. It's going to be a lot of them. We're going to have a bunch of them. And all the data that they are processing are going to go through what we call community brokers. And me with Francisco Forster from the University of Chile, we funded one of this. This is Alerci. It's a small one here. But there are other brokers, okay? And the brokers are going to sort the data out, and they're going to send it back to the community, either to other what we call downstream brokers, which receive the data that we're sorting out, and they're going to do particular tasks such as doing follow-up, like pointing other telescopes to particularly interesting sources, but also to the community. Okay, so brokers have to be able to get all this data, process it, and send it back to the community. So in terms of what do we receive? Well, what we receive are alerts. Okay, so for example, let's say I have the same images that I showed before. We have something that exploded here. And then what we do is subtract the image with the template, and we get the explosion, right? Or the source that varied. And then the next night, we're going to have, again, the same thing, and so on and so forth, right? In this particular case, we have like different images of the source as times go by. And this is what we call the image stamps. But with the image stamps, what we can do is see the amount of light that comes from these sources in time, and this is what we call a light curve. Okay, so we calculate the amount of light that comes from each of these points, and then we build this nice plot that we call a light curve. This comes in different bands, so this is basically a multi-band time series. So what are the brokers expecting to offer to the community? Well, we're going to be offering a Kafka stream. This is already happening. We're already working with this. Nowadays you can connect to our Kafka stream. We're currently processing data from CTF, which is the Zwicky Transit Facility, is one of the largest telescopes in the world, and Atlas, which is also another telescope in the northern hemisphere that is going to have a version in the southern hemisphere. So we produce a stream of annotated data that you can connect to. We do cross-matching. We look for sources that are close by to the alerts that are emitted. We provide with database access through APIs or directly to our database. We produce a lot of filtering, a lot of classifications. We calculate a lot of features, different types of features for different use cases. We have watch lists, which is basically where you say, I want to see when something happens with this particular source, and it sends an alert when something like that happens. Connect with follow-up telescopes and address multi-messenger and multi-streams data. Outliers and anomalies. We recently published our anomaly detection algorithm. data releases, so we're going to be like maybe once per year produce a data release for the whole community, like a historical data release. And of course, something that's super important is reproducibility. Okay. So just to tell you, the Vera Rubin created a call for community brokers, and there were around 15 proposals that were submitted for like the official community broker for the Vera Rubin, which is this huge telescope I mentioned in the beginning. And we made it. So Alerce is over here. There were 7 community brokers that were selected by the LSST. We are the only one on the Southern Hemisphere. Okay, there are 3 in the United States, 3 in Europe, and we are here. Okay, and all our services are currently up. You can connect to them today if you want to, and you can get access to data from CDF or Atlas. Okay, but it's not just me. It's not just Francisco and me. It's a whole team. Okay, so we have a huge team that's working on this. We started the idea that we had with Francisco in 2017. At first, we said like, okay, we can do this, right? I mean, you and me, and maybe someone else. But we quickly realized that we needed a huge team to build something like this. This is a monster. This runs on AWS right now. We're moving into a hybrid infrastructure, and we're receiving every night alerts, and we have a whole team of engineers and data scientists and astronomers that are working on the system. And of course, as you may know, there has been something called deep learning. How many of you know what deep learning is? Can you raise your hand? How many of you heard about deep learning? Okay, yeah, sort of an important time. So basically, this is the number of publications in astronomy in some of the major journals in astronomy in time that contain the word deep learning. And you can see that since 2015, which was when we published our first paper with deep learning, this started growing up like really strongly and significantly. And you can see that since 2022, this plot I made it this morning, by the way. So this is very updated. And you can see that we are kind of stuck, so there's no growing anymore, apparently. I'm going to tell you why later. But basically, everyone in the astronomy community is turning into deep learning. And I guess that in most of the communities nowadays, maybe, no? I don't know. So I'm going to briefly explain what deep learning is. Deep learning is based on on neurons, right? So if you have a neuron, which you most likely know, it's a cell that receives electric inputs and it emits electric impulses. You can connect a lot of them and you can build like a neural system, right? Deep learning is basically the same idea. This idea started like in 1940-ish, something like that. And you're going to model the neuron, and you can connect a lot of these artificial neurons and create an artificial neural network, okay? And that's it. Now, to me, deep learning is like playing with Legos. So basically, you can have a whole bunch of pieces of Lego, and the way you connect them may make something significant, right? It means something, okay? But if you have more pieces of Lego, you can create something even bigger, right? So it's all in how you connect the pieces of Lego, right? So deep learning is mostly the same. It's like, I have a problem, for example, I don't know, I want to classify between dogs and cats. How do I connect the neurons so that the neural network is able to classify between dogs and cats? Another example, I want to, for example, make a video of myself dancing ballet, and I don't know how to do it. I can connect neurons that are able to grab an image of me or a video of me and make me dance ballet, okay? It's all about how you connect them. So now I want to talk about what is a transformer. Do you know what a transformer is? Can you raise your hand if you know what a transformer is? Okay, so I'm going to explain it briefly. I don't have enough time to explain it in depth, but so let's say we want to work on something really simple, which is translation, okay? And so I have a sentence here that says, the brown dog got happy and barked at me, okay? And I want to translate it into Spanish. And the word in Spanish would be el perro café se puso feliz y me ladró. Okay? So the original way we were doing this, like maybe 10 or 7 years ago, was we created what we call a recurrent neural network. So the way you do this is you grab the word, you turn it into a vector, and then you connect neurons in such a way that I can generate a representation of that word or in some particular space. Okay? And then for the next word, I do exactly the same, but now I get the state of the previous word, and I also input it into the network, and so on and so forth. And I would expect that after the model reads all the phrase, then I will have a vector that represents the whole sentence, right? And then what I do is I grab that vector, and I do the exactly same thing, but the opposite. So it's not exactly the same thing. But basically, what we do is you create a vector of the first word, right? And you decode it into the word in Spanish. And then that vector goes into the next state, and it also receives the input from the first word, and so on and so forth. And then you can translate the word, the sentence, okay? This is what we used to do. So I don't remember, well, Google Translate, you remember, you know Google Translate, right? Google Translate like 10 years ago was using something like this. Okay? Now the thing is that maybe we're asking too much for the network to be able to get all the information from the sentence in just one vector at the end. Why don't we use the other representations of the words to try to predict each of these? So this is where the attention mechanism comes in. So the way we do this is, for example, if I want to translate L is related to the, right? So I would need, why not, when predicting L, pay attention to the, right? And if I want to translate café, I could try and pay attention to brown. And if I want to get perro, I need to pay attention to dog. And for example, when I translate se puso, I need to pay attention for both of them to got. And if I want to translate me, I want to predict me, I have to pay attention at me. Okay? So this is the whole idea. And in order to do this, we create for each one of these words what we call an attention vector. Okay? And this vector tells you how much attention you have to pay to each of the words in the input. So, for example, if I want to predict café, then I have to pay attention to brown. The vector would look something like this. And 90% of the attention goes to brown, but maybe a 10% of the attention would go to dog. I need the sentence to understand that I'm predicting for a dog, because café can be coffee in Spanish, right? And for example, if I want to predict for me, I need to pay attention to both of them, and then you say 40% of the attention goes to at and me, and maybe 10% for barked and 10% for dog. Okay? So this is the idea behind attention. Now, then this is attention, right? But there's something weird here, that the recurrences are somehow inefficient. What do I mean by this? That in order to get this vector, I need to do all the operations before that, and those are sequential operations. So that means that it's really hard to parallelize this. Okay? So the idea that was like this huge success in the machine learning field was, why don't we just use attention? We forget about the recurrences. If we had only attention, then I could learn each of the attention vectors independently in parallel. Okay? So that's what they did, and the idea is to create what we call a contextualized embedding. And how this works is that in order to predict, for example, the representation of the word barked, I'm going to pay attention to barked, but also to happy and to dog. Okay? So that's the whole idea. How do we do this? So the way we do this is, for example, we have this short sentence, el perro café ladró, okay? We turn each of these words into a vector, and then what we do is we get the same words here, and we're going to just calculate a correlation matrix. So I'm doing the scalar product between these vectors and the vectors here, okay? And I would expect that words that are related, that usually are part of the same meaning or the same context, will have high correlation. So for example, ladró and perro, so that's barked and dog, have a high correlation, okay? Because usually something that barks is a dog. I was going to say something, but maybe I'm not going to say that. Okay, so then what you do is the attention vector that I mentioned is just created by running a softmax function over this correlation vectors, right? So that means that I'm just going to make them add to 1, okay? And so then I have the same sentence again, the brown dog barked, and what I'm going to do is I'm going to multiply each of them times the attention here on each of them, and I'm going to get this vector that's the representation of that particular word. Okay, so this is the vector that represents this word, this is the vector that represents this one, and so on and so forth. Okay? Now there's a little detail here that I'm omitting and that I'm going to tell you about. It's that first, what we do is we turn these vectors into what we call a query. We turn these vectors in what we call a key, and we turn these vectors in what we call a value. So we're not using exactly the same vectors, okay? And how do we do this? We do this by multiplying x, which is the input vector, times a matrix, WQ for the queries, WK for the key, and WB for the values. And those are parameters that the model needs to learn. Okay? And well, I'm going to skip this, but just to let you know that, how do we learn all this, we also do a softmax here in alpha. So this is the alpha. Alpha is the softmax of this correlation matrix. It's exactly the same thing that I said, but with math. All right? So if we have this mechanism, now we have like a piece of Lego, or maybe not a piece, but a whole bunch of pieces of Lego that are able to pay attention to the input, right? And now what I can do is I just can grab a whole bunch of them, right? And I can build a lot of them and start connecting them. And that's what we call, so each one of these is what we call a head, an attention head. And you can have multiple heads of attention, one after the other. And this is how it works, okay? Now, I think that's important is that the way I've been explaining all this, and this is super important for light curves, that for astronomy, and I'm going to tell you about this later, but a very important thing here is that, as I have explained it till now, there's a small problem, and that is that all this would work exactly the same if I shuffle the original sentence. Can you see that? I can modify the order of the words, and then everything would be exactly the same. So that means that we're missing something, right? The context of the sentence you can vary it, and you're just counting words. Okay? So the way we're doing this, what you do is you create what's called a positional encoding. Okay? And this is very important. So for each word, you have an index. I'm going to talk a bit more about this later. For each word, you have an index, and then that is turned into a vector. And that vector encodes the position of the word. Okay? And then that vector is also used with the vector that represents the word, and you join them somehow. You can add them up, or you can concatenate them. Okay? And then, ta-da, we solve the problem of the position of the word. Okay? So why has this been so popular? Okay? Why ChatGPT uses this? Okay? And basically because it had this very simple idea. I mean, now that I tell you the idea, it's like, oh yeah, super obvious, right? I could have thought about the same thing, right? Or maybe not. But the thing is that it has broken all the benchmarks in natural language processing. An example of that is GLUE. GLUE is a challenge that has nine different tasks that are related to natural language. Okay? And I'm going to show you this. So this is the performance of different models in GLUE in time. So before OpenAI, okay, you all know what OpenAI is, right? Yeah, the creators of ChatGPT. Before OpenAI, the benchmark was in around 74%. The first GPT in 2017 raised this to 75.1. Okay, so it's 1 point, great. Not such a big deal, but still. But then in 2018, BERT appeared, and this was a huge impact. In a year, from 2017 to 2018, the benchmark raised 7 points. Can you see that? I mean, this is something that usually doesn't happen in artificial intelligence. That in a year, you raise a benchmark 7 points, right? And the year after that, it raised six more points, okay? So this is what we call a revolution in artificial intelligence, when something like this happens. And it's not the first time that happened. In 2012, it happened with image processing. But this was all thanks to the transformer architecture. And this is a plot that shows another benchmark, which is the squad benchmark, but it's also the same types of models. You can see that around 2018, this raised up, and then this is what we call the revolution. And nowadays, this benchmark, this particular benchmark, yesterday I looked for it, it's still at 90%. So since 2020 until now, we haven't made any progress on this, okay? So now that we know what a transformer is and why it's important, now the question is how do we apply it to light curves, okay, or to astronomy data? I have to make a disclaimer. Nowadays, we're applying this to a lot of astronomy data. We're applying it to images. We're applying it to light curves, which is what I'm going to talk about. We're applying it to spectra, to a lot of things, okay? So I'm going to talk about how we apply this to light curves. So if you remember this slide I showed before, we're working with sequences of images, and then we usually create a light curve. Okay, you can work directly on the sequence of image, but that's for another talk, another day, all right? But for the case of light curves, the question is how do we adapt something like the transformer, which it makes sense, right? Like a sentence is a sequence of words. This is a sequence of observations, right? So how can we adapt something like this to a transformer to something like this? So if you think about it, the transformer in natural language processing has two main components. You have the sentence, right? The brown dog became happy and barked at me. You grab the word, the, transform it into a vector, and you have the position of that word. That's the first word. So you put that I equal 1 through a positional encoding, which is also, by the way, a neural network. Okay? It depends on how you build it. Yeah, some people don't. But then you add them up, right? And then you have another word, brown. So you have the vector that represents brown. You have the position 2, and then you run that through a positional encoding, and you add them up, right? You can add them up or concatenate them or do something even fancier. And so on and so forth. And then you have I equals 3, I equals 4, I equals 5. And that all goes through this transformer machine, this multi-head self-attention mechanisms, okay? A light curve, on the other hand, is something like this. So you have time on the x-axis, the flux, let's say the brightness, how bright the object is. On the y-axis, the astronomers are going to kill me here in the room. And what you do is, let's say that this is the real light curve, but you don't observe everywhere, right? So this night I observed here at this time. Maybe tomorrow I observe this, and maybe a week from now I'm going to have another observation here, and maybe next week I'm going to have another observation here. Okay? So now what we do is we grab the flux, turn it into a vector. Actually, this can be the flux plus the noise plus other metadata that's around at that time. Okay? But let's say we have only the flux. The flux, you turn it into a vector. Then you have time, you put the time into the positional encoding, okay, which is slightly different. It's not the position of the observation. It's not 1, 2, 3. It's the time at which you observe that. And then you do this, so on and so forth, with time 2, and then you put all that through these multi-head self-attention blocks, okay? And this is super important because the way the positional encodings work for astronomy are slightly different than the way they work for natural language processing, because time is continuous, right? So you can have time, I don't know, 1.2345 days or something, right? So now I want to talk about foundation models, because this leads us to what we've been publishing or doing during the last couple of years. So a foundation model is a model that's trained on a lot of data in such a scale that it can be applied then to a wide variety of tasks, okay? And one of the first ones that appeared here is BERT, okay? And I'm going to tell you how BERT was trained, how BERT existed, and then I'm going to tell you how we do something like this for astronomy. So BERT, what it is, so the first thing is that BERT was trained to generate a representation of text that's independent of the task you want to apply that representation to. Okay, so it's not about translation, it's not about classification, it's just an embedding that represents the text itself. Okay, so if you have something like this, the brown dog became happy and barked at me, okay, what you want to do is to throw all this data into a transformer and then get these representations, this contextual representation of each of these words, okay? And the way they did this is by using something that's called self-supervised, and it's basically the model self-supervising himself or itself. And the way they did this is they started by masking some of the input, okay? So I masked them, and then I tried to predict those words through the representation of the model. I'm not sure if you see this, but this is super smart, right? I don't need a label for the data. The model itself trains himself to understand what the data is, okay? And then what you do is you try this by predicting through a softmax function. And BERT, the original BERT, masked around 50% of all the tokens in each sequence at random, okay? And this is what we call a masked language model, okay? So what we did, and by we, I mean my student, Cristobal, what he did was he applied the same technique of BERT, and he created what we call Astromer. And this is a transformer for astronomical light curves. And basically, it's the same idea as BERT. It has four heads that are concatenated in different layers. So they're one layer after the other, each one with 4 heads. And it was trained with macho data, around 1.5 million light curves in the R band. And what Cristobal showed was that by using something like this pre-trained model, we are able to become better than any other model in the literature at that time. This was 2022. It was accepted 2022, but published 2023. Okay? And then we said, okay, that's great, but what happens when the LSST starts? There's going to be something weird, that the cadence is going to be different. I mean, the way the amount of time between one observation and the other is going to be different. And actually, it may be different after a year the LSST starts, and maybe after 2 years they're going to decide, well, I don't know, I don't like this cadence, I'm going to do some other cadence, okay? Of course, it's not like that. So we said, what happens if we change the cadence, okay? And what we realized is that it all leads to the positional encoding, because the positional encoding is the one that's modeling the cadence, right? So what he did, this is Daniel, another student. Whoops. Okay. So this is a paper that got accepted at ICML. So it's called Playing with Positions and Attention. And Basically, we pre-trained the model with the 1.5 million light curves from Macho, and then we, where should I put it? There. And then we apply this to a subset of 500 light curves per class that was labeled, and then we trained the classifier in this. But we also applied it to Ogle and to Atlas, other surveys. And the other thing that we did was that for this Macho labeled, we said, what happens if we reduce the cadence? Okay? And the way we did that was by randomly removing 1/4 of the observations, then 1/2 of the observations, and then 3/4 of the observations. Okay, so we started removing data to see how much did that affect to the model. And the other thing that Daniel did, I mean, it took him a lot of time and effort. So, by the way, Daniel is right now at Harvard, so he's not here. Most likely he's not listening to me, or maybe he is. But what he did was that he trained a lot of different positional encoders. Okay, we can talk about this later if you want to, because it's going to take me some time. But there are different positional encodings. There's one that includes a recurrent neural network. But also, we created our own positional encoding, which we call P, which stands for positional encoding on attention. And it's basically the idea is that instead of putting the positional encoding at the first layer, right, what we did is we did all the attention on the fluxes first, and then we put the positional encoding on top of that. And these are the results that he got. So this is the F1 score for the different data sets. These are the different positional encoders. And the kind of things that he found was that training the positional encoding is instead to just keeping it fixed, which is something that's really common in the field, to keep the positional encoding fixed instead of training it. So training it suffered less degradation with sparser light curves. So these two are trained, and you can see that by training the positional encoding, then it degrades less in terms of the number of points in the light curve. And the other thing that we found is that P, which is our positional encoding, performed better on Ogle, okay? And Fourier performed better on Atlas. So this is important. Here, all these experiments are only related to the cadence, to the time, but the fluxes, the distribution of the fluxes are the same. But here, the distribution of the fluxes also change. Okay, so the next thing I want to talk about is this astronomical transformer for time series and tabular data. Okay, it sounds like a long name, but it's an excuse to name it AT-AT. Okay, you know what AT-AT is? Have you watched Star Wars? It's this big. I'm going to show a picture of that later. Okay. So remember I told you about this? Well, what happened is that we're here, Alersi, and the dark energy science collaboration of the LSST created a challenge, which they called the Elastic Challenge, Extended LSST Astronomical Time Series Classification Challenge. And basically what they did was that they simulated a stream of the LSST, and we had to, the brokers, we had to classify everything, okay? And this is the taxonomy they used, this one on the right. This is the different models that they use. But there were things like supernovas, kilonovas, microlensing, AGNs, RR Lyrae, Cepheids, eclipsing binaries. It was a whole slew of things. Okay, and our proposal was this brand new model called AT-AT, and basically what it does, it's formed by two transformers. One transformer is a light curve transformer, and the other one is a quantile feature transformer. So let me explain this to you. This was not my idea, by the way. Huh? This was the idea of Nicolás Astorga, who is a student that he's currently doing his PhD at Cambridge. But the thing is that what he thought of was, we get the data from the light curve, we put that into a transformer here, and then we also have features, that some features we calculate them and some others are metadata, okay? And that go through what's known as a tabular transformer. And then you connect them all. So if you have the representation for the light curve and the representation for the table, then you can just concatenate them, right? And then you run that through a classifier, okay? And well, it has some ingredients. I'm going to go really fast on this because I'm running out of time. But the positional encoding was switched was changed for what we call time modulation. And it's basically you grab, let's say, the flux. This is not the flux, but it's all the data that comes from the observation, including the flux. And we modulate that by a Fourier series, okay? And we add also another Fourier series, okay? And all these parameters are learned. And in terms of the features, like the tabular data, what we used was a feature tokenizer that Nicolas modified in order to just add a quantile transformation, okay? And with that, we were able to win the challenge, and this is an AT-AT, in case you don't know, okay? Now you know it, right? And so we were able to win in terms of the classification metrics, the challenge, and this is our confusion matrix. Of course, there are some confusions there, but well, we can talk about them later. So some takeaways. The first thing is that I hope I convinced you that transformers have become the state of the art in many fields, and that's including astronomy. Foundation models for light curves are already a reality, and the future, well, what do we want to do with this in the future, right? And if you think about things like ChatGPT, what ChatGPT is doing, it's working on multi-model, on multi-task models. And so we're currently developing algorithms to work on multi-streams, multi-messengers for different tasks. And we're thinking about, let's say, we're going to input spectra, images, light curves, everything into the model. So remember this slide? I told you this was the boom of deep learning in astronomy. Well, now we have a boom also in transformers in astronomy. So since 2021, the number of papers in astronomy that uses the word transformer is increasing. So these are the papers containing deep learning or neural network and transformer in all these journals. Thanks. That's it.
So, questions? That was faster.
I have this one. Okay, so let's no, but I can use this, right? You want to? Oh, okay. Yeah.
Next. Go ahead.
Hi, thank you very much for the talk. I have a question about the last thing you mentioned about the foundation model taking multimodal data and do multitask. I guess like you want to combine data from these different surveys, like as you said, photometry, spectroscopy, light curves, and everything all in once to make a prediction, like estimate parameters for objects, right? Mm-hmm. I'm sure it's the question everyone asks when someone mentions transformers. Like, how do you, if you have an idea, how to avoid or reduce hallucination in the estimation of parameters?
Okay, so thanks. So hallucination is something that happens with generative models when you're generating data, right? So that's something that happens with ChatGPT, for example, that it's only generating data. It's not like ChatGPT does not like have a conscious way of thinking what word is going to be the next one. It's just sampling from a distribution and generating the data, the word that comes after that, right? So if you're thinking about generative models, then you may have a problem with hallucinations. One thing that we're working on right now is, so the way you solve that is you have to evaluate the model in a way such that you can discover those hallucinations, okay? So for example, one thing that we're working right now on is, for example, we have, in Alerce, we have a very complex database we have two databases. One, it's a standard Postgres database, and that's a relational database. And we also have a NoSQL database, a Postgres SQL. So what happens is that whenever someone goes into our system and needs to do a query on the database, it needs to know a lot about them, right? So we're using natural language processing so that you can write, I want to get all the objects with such and such magnitudes or whatever. And the model turns itself, this is a language model, it turns that into a query. Okay, and the way we do this is before we run that query, we evaluate it, the query. I mean, is it going to run? How long is it going to take? And stuff like that. And we're really careful about that because that's where a generative model comes in. How would I use a generative model for something like this? Maybe I would think about, for example, let's say I have the light curves and I want to generate the spectra out of it. And then that's when things get a little bit tricky. And most likely, if we do it just like blindly, it's going to be generating, it's going to be hallucinating. Yeah. But this is not giving explanations, right? I mean, if we input, if we connect something like a natural language processing model to this, trying to explain us why it generated such spectra, then most likely we're going to have that problem.
Thank you very much.
Thank you very much. Very interesting. I have one comment and one question. So the comment came to my mind when you mentioned this revolution with the evolution of the percentage with BERT and everything. And for those of you who speak French, I'm sorry, but there's a very, very interesting leçon inaugurale at Collège de France that was a couple of weeks ago by Benoît Sagot, the author of Camembert. Okay. Camembert is another nickname for cheese in France, as you may know. And again, some of his words were very similar to yours at this moment. So for those of you who can see this video, it's online, it's on YouTube. It will probably be translated in some time, but for the moment it's only in French. So that was my comment. But again, thank you very much for the very clean explanation. And now a question regarding... So for the light curves, when you explain the transformer, so you explain that you put T1 and T2, etc., instead of 1, 2, 3, 4, which provides some kind of dynamics to the model. Maybe it's a very naive question, but what would it make to change that with the derivative of the fluxes into the transformers? Would it be something equivalent or better or worse?
So that's a very good question. So for example, one thing is how you input time. The other thing is how you input fluxes. The derivative combines both, right? It has the difference in flux and the difference in time. You can, so if you think about the derivative itself, it's, you can think, let me go back to the picture of the light curve. I need the light curve here. All right, so the derivative, it's related to the time at which the function was measured, but also to the flux, right? That's what you're saying. So, but in principle, if you have time into the positional encoding, then the derivative is another feature for that particular observation at that particular time. So what we usually do is if we want to input something as difference in fluxes, or the derivatives, because it's the difference in fluxes over the derivatives in time, we input that on the feature space. So that would be here. For us, it's like a feature at that particular point. And we do it, by the way. Not exactly the derivative, but the differences.
Awesome. Any other question? So I have a lot of questions, but we are running out of time. So I will just put one, and maybe it's for a discussion during the coffee. I will ask you more questions during the coffee, but transformers half of the problem because solve the complexity at training time, but then they become really expensive at inference time. Do you see it will impact? You have like process a lot of data really fast. Do you see it will impact your inference capacity? You're like to apply it?
So I'm not sure what you mean by being
they are really
expensive in inference time. Are they?
They are.
Why do you say
They have
that?
an n-square complexity. So at the inference time, they are really slow. No?
Yes, but the recurrent neural network also is n square, right?
No, at inference, not necessarily. At inference time, they are order n. You just go through the network.
Okay.
And
Okay.
to compute the attention, you need to
Okay.
compute n by n.
Yeah. But it depends on many things, right? It depends on the number of neurons of all of your networks. So I was thinking about n squared because you have n neurons that you're connecting to n neurons after that in the recurrent neural network. So that's n squared. Okay. But in terms of inference time, so first, this is super important that combining a recurrent neural network with attention mechanisms gives you more capacity on the model. So that means that your model is better, but you cannot train it in parallel. Okay? So you can, nowadays that we have a lot of data, we are able to train it in parallel, the transformer, but not the recurrent neural network. Okay, that's number one. Number two, in terms of inference, the difference between, in terms of how expensive it is to do the inference of a recurrent neural network and a transformer is not that high in the number of parameters. If you think about this, nowadays, let's say ChatGPT has billions of parameters, right? That means that the data has to run through all those billions of parameters. Yeah. So
Well, actually, no. They have tricks to try to, use other forms of attention. I think, my opinion.
yeah, they can crop it.
But
So they have different ways
yeah,
of cropping.
they don't use the full matrix and all of that. I am playing with advantage. The thing is that a couple of weeks ago, I read a paper that was really, really interesting. That they imagine that this is like these beach chairs that you unfold, no? The transformer is like the beach chair folded. You train it, and then you unfold it as a recurrent neural network. It was really efficient. This is how, in my limited mind, I managed to understand the paper. But it's a very good idea. And of course, they claim that they are better than, they are as good as transformers at training time. So maybe it's a good thing to start to look at these things. Yes, a recommendation. Any other question? We can talk later about it. Okay, thank you very much.
Okay,
Guillermo.
thanks, Steve.
Okay, our next presenter is Aldo. Are you here? Welcome. Se va a poner solo. Ok, perfecto. Bueno, no, hay alguien, ¿no? Pero... Do we need to do it by hand? Ah, no. Well, in the meantime, I will introduce Aldo. Aldo obtained his PhD in physics in 2001 from the University of Ulm, Germany. After a postdoctoral research stay at the University of New Mexico, USA, he joined the University of Concepcion in 2003. He's currently a full professor here and directs the Millennium Institute for Research in Optics. And he's going to present us a very interesting topic, optimal estimation of quantum states and unitary transformations. Thank you very much.
Okay, so thank you very much for the invitation to participate in your meeting. This talk is about quantum mechanics, and I don't know how much you are about on quantum mechanics. So probably this will require a small crash course on the subject, okay? So quantum mechanics has been, since its creation about 100 years ago, a very debated theory, mainly because the fundamental consequences on our understanding of the universe. Quantum mechanics tell us that there is no determinism in this universe, that everything is probabilistic at a fundamental level. And because of this, it has created a lot of troubles in our understanding of the universe, and in particular in the way we say the things are. Now, from the mathematical point of view, quantum mechanics is a rather simple theory. It's just linear spaces and matrices. That's all. Okay? So when I say a quantum state, I am just talking about a complex vector, a finite vector, with coefficients which are complex numbers. That's a quantum state. And when I want to manipulate this quantum state in time, I use a unitary matrix which acts onto it and create the state of the system, the vector, in the next time. That's quantum mechanics. Now, these two objects are related to a third object, which are measurements. Measurements are just set of superoperators, operators that act onto matrices, and that's it. So that's the whole hierarchy we have. We have vectors, matrices, and superoperators, and that's it. That's all the set we need to know to understand what I am going to present today. Now, quantum mechanics has also technological applications currently. You have heard something probably about quantum computing and quantum cryptography. These are applications of the quantum theory, as well as diode lasers and the laser itself. These are quantum objects. You cannot explain the laser without quantum theory. You cannot explain color theory without quantum theory. You cannot explain transistor, like this machine here, without quantum theory. So these are applications of quantum theory. Now these days there are new applications of quantum theory, quantum computers and quantum cryptography. Now, before applications, we need to know how to control systems. And in order to control systems, we need to decide how good we control these systems. So we have to be able to say, okay, this quantum system is in this state and not in this other state. So in principle, we need to be able to estimate what the state of an actual quantum system is. And that's what I'm going to show you now. Few strategies to decide what is the state of a quantum system and what is a unitary transformation generated by a machine operating onto a quantum system. So these three strategies I'm going to show you now are feature symmetric measurements. These are measurements which have two very beautiful properties. First, they saturate the quantum Kramer-Rao bound. So they are wonderful measurements. They are the best measurements we can find. And they provide an accuracy which is more or less the same for all the parameters that you are estimating. Okay, so you are very balanced, very well balanced. Then I am going to show you high accuracy adaptive quantum tomography for high dimensional quantum systems, something which sounds very complicated, but the idea is that you measure a quantum system, you get small amount of information using small sample, and from this you deduce what should be the best measurement to increase the accuracy of your estimation. And then we will review something called optimal estimation of high-dimensional unitary transformation. So now we will go from states to unitary transformation to matrices, and I will show you how to estimate a unitary matrix in the best possible way. Now, as I was telling you, recently it has been shown that pure quantum states, these are vectors in a Hilbert space, can be estimated using these feature symmetric measurements. These were invented by the Quantum Information Group at the University of New Mexico a few years ago. So far I remember it's 2016 more or less, okay? These work as follow. They require a priori information in the sense that you know that the state you are looking for, the state you want to estimate, it's very close to a state that you already know. This sounds a little weird, but it's the most common situation in a laboratory. Because in a laboratory, you want to create a well-defined state. You have a target state, and you set up your experiment to create this state. But because inaccuracies at the experiment, such as, for example, noise, so you are doing the experiment, and in the hallway, outside of your lab, you have hundreds of students running from one way to the other, creating vibrations, and because of that, the experiment is not ideal. Okay, so there are some error sources which slightly change the state you actually create at the lab. So this is your appearing information. So you know that you are close to the state you want to create, but you don't create exactly the state you want. Okay, so they use this appearing information to create a set of measurements that allows you to saturate the quantum Kramer-Rao bound, which in this case takes the form of the Gilles-Mazar inequality. How works this? You have here an unknown state. Psi is anytime you see a psi, that's a quantum state. Okay, so you have a quantum state expanding a certain basis. The state 0 there on the first line is the state that we say we know already. It's our a priori information. So the state psi is very, very close to the 0. Now, using this information, we can create a measurement, which we call a POVM. That's the most general measurement allowed by the rules of quantum mechanics, and which has to fulfill a certain condition. Basically, that it is that this matrix on the last equation has to be 0. All the elements of this matrix has to be 0. If you achieve this, then this POVM is a feature symmetric measurement, which guarantee you that when you use it, you will estimate the state you're looking for with the best accuracy that you can achieve according to the rules of the quantum mechanics. You can do it better. So this is a benchmark in nature. If you are able to do this, you are doing the best possible. That's the best result you can get at the lab. Now, what we did, we created an experimental setup that allows us to implement these feature symmetric measurements in reality. So we have this at the laboratory. How this works? Very simple. We use optical waveguides, optical fibers. Each optical fiber represents the path of a photon. That path is one state of our canonical basis, which expand the quantum states. So our quantum state basically is a photon that propagates across several possible paths. That's the quantum state that we want to reconstruct. And somehow we twist the optical fibers. We make them very close, then we set them apart in such a way that we can manipulate how the light goes from one path into the other, until we create an experimental step that at the end allows us to implement these feature symmetric measurements. Now, because we have certain constraints on the lab, we cannot create a perfect feature symmetric measurement, just an approximation. How good is this approximation? Well, the C matrix in the slide before had to be a null matrix, had to be a 0. We don't reach a 0, we just reach a 0.6. Okay, so we are not a 0, but we are slightly close to 0. What do we get? Well, here in the pictures, you see here on the y-axis, it's the infidelity. It's our measure of the accuracy. And then in the x-axis, you have the size of the ensemble, the number of times that you repeat your experiment to create your sample and infer from this sample the quantum state. Now, the black line represents the Gilles-Mazar lower bound, or the Kramer-Rao inequality. And the dots, our experimental result. The pictures are in log-log scaling, so that's because the error bars are so huge. But if you watch very closely the numbers, you will see that these are very slow numbers, very small numbers, okay? Now in the 3 pictures here at the right, you see that the error bars become very, very, very slow, and that our experimental results tend to follow the prediction by the Gilles-Mazar lower bound. So in principle, we are very, very close, and our experimental realization point out that it's, you have here, this is red. Yeah, it's good for you because I can't see red, sorry. I'm colorblind. Okay, so I will try to, okay, yeah. Maybe I can use the hand. Okay, so these pictures here, they are linear scaling, and in this axis, and then you see how the experimental data just got on top of the theoretical prediction. Okay, so our experiment is verifying these feature symmetric measurements. Now, you say, okay, you have to use this a priori information. So you have to know that the state you're looking for is very, very close to the one you have in the lab, to a priori information. But what if you don't have this a priori information? What can you do? Okay, there is a trick which is very well known in literature. You say, okay, I am going to assume that my a priori information is this state. Maybe it's not this one, but I'm going to consider that it is this one. And then I am going to measure the feature symmetric measurement for this a priori information. Then I will get some information. Using that information, I'm going to create a new guess for the state, and I'm going to take this guess as the a priori information, and then I will iterate. And then when I do this, you will see here that the infidelity, after a certain number of iterations, start to become very, very close to the Gilles-Massal lower bound. Okay, and this is for dimension 2, and this is for dimension 4. Okay, so we know that this works for almost any dimension for a Hilbert space. Okay, so in principle, even if you don't have this a priori information, you just repeat several times, and then you get a very good estimate of the state you are looking for. How many times? We have a conjecture, and that's the number of times you have to repeat is a number which is linear in the dimension of your system. So you have a qubit, you have to repeat just two times the experiment, and then you will get a very good estimate. If it's 10, then you repeat 10 times, okay? We haven't been able to prove this from the theoretical side. We have been working very hard on this, like 1 year, but without success. So we're still trying, but probably we will spend 1 more year on that, and then we will just give up. That's life. Now, we have already written a small summary with our results. This is a collaboration with Gustavo Lima and Stephen Warburn here at the Universidad de Concepción, and Luciano Pereira, which is one of my former master students, which is now getting the PhD at Madrid. Now, we have a family of states in quantum mechanics, which is much more larger than the pure state that I was using in the previous scheme, and these are the mixed states. Mixed states are matrices, so we go from pure states, which are vectors, to matrices. So a matrix can also be representation of a quantum state, and we need also for this special class of states a method of estimation. The problem is that there are no feature symmetric measurements for mixed states. One can prove that. That's a theoretical result. Okay, so when we go from pure states to mixed states, which are the most probable state in reality when you go into a lab, then in principle you cannot use feature symmetric measurements. These are reduced to very, very particular conditions, very, very particular experimental setups. Okay, so in general, we have to create methods to estimate states. We consider these mixed states. In order to do that, we have created a method that allows you to estimate density matrices with a small penalty, at most a factor 2 with respect to the Kramer-Rao lower bound. And that's the best that currently somebody can do in quantum mechanics. So there is no better estimation strategy for mixed state than the one we invented here in Concepcion. Okay. This is just a bunch of theory, which I'm going to skip because we have few time. Okay, so how this works in the practice? We have measurement bases, which is equivalent to say that we have several different experiments that we have to perform to be able to estimate this mixed state. So estimating mixed state, it's much more complex, much more difficult than estimating pure states. Okay, in principle, there is a scaling which goes like the dimension. It's linear in the dimension. Okay, the effort that you have to do to estimate a mixed state when compared to a pure state. So it's much more difficult. Okay, now we can create a set of bases. How many bases? The order of D, the dimension of the system, which allows us to estimate this mixed state with an accuracy which is very close to the quantum Kramer-Rao bound. We did also an experiment here also in Concepcion, to verify our results, and we get this. Here you have the number of counts in the experiment, which is more or less like the size of the ensemble. It's proportional to the ensemble size. And here you have again the infidelity, which is our measure for the accuracy in the estimation process. And you see here, this is the quantum Kramer-Rao bound. This is twice the quantum Kramer-Rao bound, and our experimental results are more or less aligned with the theoretical results. Why more or less? Because this is an experiment that has to run for at least 10 days simultaneously. So the experiment has to be run in the lab without interruption for 10 days. And it doesn't work during winters, it works only during the summers because the temperature conditions. And we did this in a time in which the electric power at the university was not very constant in the summer. So sometimes the experiment was just about to finish and power went out and we had to start over and over and over. So it took like 6 months to get 10 days of uninterrupted data to get these 4 points of data. Okay, so it was a nightmare. And that's explained a lot why the results are not very conclusive. Okay, and we are not planning to do this again, so we are not going to repeat this. It was enough. We also have a manuscript on this that you can find in Archive. And finally, we have also a method to estimate unitary transformation. So a unitary transformation is a system that acts onto a quantum state, okay? And you also need to be able to estimate this unitary transformation. Why? Because usually this unitary transformation is a machine, like a quantum computer. So you have probably heard a lot of quantum computers, which are a bunch of qubits, but they are not just the qubits, they are the quantum gates that act onto the qubits. And these quantum gates are unitary transformations. If you want to know how good your quantum computer is, then you need to estimate how good your quantum gates are. Why this is important? Because we need to go over a certain threshold in the accuracy of the quantum gates. If you want to reach universal quantum computing power, then our quantum gates need to be better than errors in the order of 10 to the minus 7. And currently, we are in the order of 10 to the minus 2. So we are far away, okay? But in order to be able to say this, you need a method that allows you to establish what is the error of your actual quantum gate, okay? Now, this method allows you to do this, okay? So this is a little bit technical. We just take the unitary transformation, we expand it using a linear combination of operators x and z, these operators here, these coefficients characterize your unitary transformation, and this here is just a basis for operators in dimension d, okay? Now we can create a quantum circuit using these x and z operators. You see here is the circuit. This is not a complex thing, but it's not the usual stuff too. So we apply the quantum circuit onto the unitary gate we want to estimate, and this circuit transforms this unitary transformation here into a quantum state. So it takes the unitary transformation, which is something that acts onto a state, and transform it into a state in such a way that the coefficients of the state are exactly the same coefficients as the coefficient that define the unitary transformation U here. And then, because you know how to estimate states, you can now estimate the unitary transformation. Now, if you follow quantum estimation theory and calculate the fission information matrix and the quantum fission information matrix, then you will realize that using exactly this quantum circuit, then you will get that the classical fission information matrix is exactly equal to the quantum fission information matrix, which is an indication, it's a demonstration that you are saturating again the quantum Kramer-Rao bound, which is the best that you can do. So using this approach, we can estimate unitary transformation with the best possible accuracy. This result also holds in higher dimensions, beyond 2, when the unitary transformation is close to the identity. It doesn't work for any unitary transformation. You need a priori information. You need to know that the unitary transformation you want to estimate is close to the identity. Is this something that you will see in the experiments? Yes, definitely. There are many quantum gates that work in this way. Okay, we have continued our work on this, and we know now how to extend this to any unitary transformation. But you need some a priori information. Okay, so you can do better. You can do it for any unitary matrix, but you need to use a certain amount of a priori information. And we have also tested this method in the IBM quantum computers. We have used it to estimate a single qubit unitary gate. In this here, you see again the fidelity, the ensemble size. This is the performance of our method. It provides a fidelity which is extremely very close to 1, and this is a standard quantum process tomography. It's the process used by IBM to characterize the unitary gates. And you see that our method it's much better here in mean and in median. The numbers agree perfectly, just one onto the other. And when you allow for errors, when you assume that there are errors in the gates and so on, then our method it's again better than the current one. So it's a very reliable method. We also know how to implement this method in our lab. We have something called a quantum switch. It's a new type of machine that allows you to create superpositions of different temporal orderings. It's like traveling to the past and to the future. It's a weird thing, but we know how to use this machine to implement this method and estimate unitary transformation, and that's coming probably next year. So with that, thank you very much for your attention.
So, questions?
Yes.
Right. How does it change if you use a more massive particle, like an electron?
With
Or a
electrons.
neutron, or a neutron.
A neutron.
Yeah, something that has no charge but has mass.
Yeah. My guess will be that this circuit here, for example, if you want to estimate a unitary transformation acting onto a neutron, for example, you can transform this into an interferometer and use neutron interferometry to estimate the unitary acting onto the neutron. Something like for example, the cow experiment, you know, this, where they show this gravitational time delay acting onto neutrons.
Right.
It should be close to that, but very difficult.
Yeah, I guess so.
Okay, it should be something very, very difficult.
Yeah, I guess so.
Because you need more path. Let's say it's not just a two-path interferometer, 2 arms. You need something with more arms.
Yeah. I guess you need an accelerator. No, maybe not.
Maybe just you need gravity to do that.
We have very little time. Do you? There was a question.
Okay, thanks, Aldo, for such a great talk. I felt like an undergrad again. So you talked about the dimensions of the system, right? And I think you mentioned like a qubit has 2 dimensions. Is that correct? Yeah. So I think I got that. But how do you increase the dimensions? And I mean, you talk about high-dimensional transformations, right?
Yeah.
So what do you mean by high-dimensional? How high those dimensions are, and why are those dimensions that high?
Well, the simplest example is the quantum computer. In a quantum computer, you have many qubits, okay? And that means that you have one qubit just with another qubit at the side, okay? And you put several qubits together, and then you increase the dimension of the system, okay? But the increase is, let's say, it's exponential in the number of qubits. It goes to as 2 to the power of n. So you have 100 qubits, then you have 2 to the power of 100, and then if you want to simulate that kind of system, any computer runs into troubles. If you make it this 2 to the power of 10,000, then it's gone.
When you talk about a high-dimensional regime, how many of them are? How many qubits?
Okay, if you have 10 qubits, then any computer get and slow down massive. Let's say it's very very difficult to study that stuff. Okay, with just 10 qubits. It depends on the software. It depends on the programming language. But with 10 qubits, you already goes into the hour regimes. So you have to wait for an hour to get the result. Okay, so if you go into hundreds, then it's a problem. But for computers, you need probably 10 of thousands of physical qubits to have a real machine.
Well, thank you very much.
Okay.
Amazing presentation. Thank you for. And now, sorry. And now we have another very interesting presentation from Neil. Neil Nagar is a professor at the Universidad de Concepción and director of the Titans Millennium Nucleus. He's a founding member of the Event Horizon Telescope and Next Generation EHD collaborations. Nagar obtained his engineering degree at Pilani, India, and his PhD at the University of Maryland, College Park, USA. His research interests range from supermassive massive black holes, galaxy evolution, and ultra-high energy cosmic rays. I love it. So go ahead. Thanks.
Thank you. Thanks, everyone. So really, as you can imagine, I'm here to talk about on behalf of a lot of people. It's a very big collaboration, and that's why it's a nice example of the pluses and minuses of large international collaborations. So primarily from the Event Horizon Telescope, the next generation upgrade, of course, we get a lot of support here in Chile and working through Titans. And so it's to talk about some of these images that you might have seen, but really to look at what it could mean for collaboration. This was the original, I was working on this from 2000, finally finished my thesis maybe 15 years late, and then this finally appeared. So it was a long run. We started a long time ago. If you look at those white dots, those are the telescopes that we had. Specifically, I point to Noima in France and IRAM, which is run by France. It's a collaboration between Spain and France, physically in Spain and France. And then ALMA and APEX here in Chile. So there were very few telescopes. And if you look at the simulation, what we expected to see was what's labeled as expected. There's kind of a shadow, a ring, and a jet leaving M87, a nearby galaxy. What we actually saw was terrible, right? I mean, it was still very exciting, but it was just very, very little detail. And so while that was exciting and it was the first direct evidence of a black hole, we'll see what that means. We do want to make it better, and that's a bit of the story here. So what were we seeing? Right now, with the Event Horizon Telescope, we have two images, and those are those two donuts. Again, very ugly looking things. But really what we're seeing is shown in these two schematics here. It's light bending around a black hole because the black hole acts as a lens. And so what we're really seeing is the back of the black hole, and the light from the back, here's the black hole. The light from the back gets bent around and then comes to you. The light from in front actually gets bent around the other way, even if it tries to come to you. But it's a bit more complicated, of course. Some photons go all the way around and then come to you. Some go around a couple of times and then come to you. But effectively, what you end up seeing is a shadow, because the ones just in front and behind do not come to you, and a very bright ring around because of a pileup of a lot of columns that happen to come to you. So, I mean, there is much more detail on this. As I mentioned, some of the photons started from here and got to you. Some started from here and got to you. And as they go more and more around and then finally come to you because they're just off a stable orbit, the ring becomes finer and finer. We want to get that. So what we really see here is a mix of all of these different kinds of orbits. And we should get to what's called n equal to 2. That's what we want to get to, because that's a very fine ring. There you can test general relativity, all of the theory of gravity, because the trajectories that these take depend on gravity. And if they don't come out to be what you expect in GR, then you have to change your theory. So what we've done so far, after a lot of work, is actually still very little. 2 black hole shadows with their bright lens rings around them, and a few other powerful supermassive black holes, which instead of seeing the material falling onto the black hole, and I should mention this is 230 gigahertz, it's millimeter wave astronomy. What we're seeing is actually just gas, very hot gas orbiting the black hole and falling in. and it's hot enough that it's producing synchrotron and thermal emission, which is what we see in the radio. We can measure polarization, which is you put on your sunglasses, you're just seeing one polarization of electromagnetic radiation. The direction of the polarization gives us the magnetic field. So we also have circular and linear polarization, which tells us how the magnetic field is wrapped around, which also tells us how the black hole, whether the black hole is spinning or not. And then some others launch jets. Instead of just eating food, black holes are messy eaters. More than 90% of whatever falls onto them is thrown out, typically in two very collimated jets, which is what is seen there. But that's the past. What we want to do is something called a next generation upgrade to the HT. You see many more dots. All of the blue dots now are new telescopes that we want to put in. And the reason is because we do interferometry. We don't actually make images, we do Fourier transforms. Each pair of telescopes measures a Fourier transform of the source distribution. And then we use a lot of magic and fudges to kind of make an anti-Fourier transform, an inverse Fourier transform to make an image. With all those extra new dots, we'll do much better. And now you see the expected GRMHD simulation. So that's a magnetohydrodynamic simulation with full general relativity. And you see what we expect to see with this telescope. They're almost the same. So with this, we could really, really see what's happening. And this is the plan that's going on. We're trying to get $100 million from the NSF right now. And so we actually printed a special issue in Galaxies with all of these papers together to say we're worth $100 million. And you could read that if you'd like to. And so basically what it's trying to do is a telescope the size of the Earth. We've pretty much reached the limit. There are already plans to put something in space. This has been done before at lower frequencies. We need to do it at higher. Because that's the only way then to get to a higher resolution. So this is it's a good example of collaboration. It's a forced international collaboration because we need telescopes all over the Earth. And so it's very northern hemispheric centric. There's only very little there. There are 6 continents, more than 25 countries, more than 60 universities. We started off very few, maybe 25 a long time ago, and now there's more than 350. And more than 10 telescopes. It keeps increasing every day, so I didn't even want to write a number. The actual inversion was very small because it typically used existing telescopes and upgraded them to be worked into here. But at this point, we've run out of existing telescopes, which is why anything new has to be a little more expensive. So if we zoom in, there's actually very little in South America. There's the 2 telescopes, ALMA and APEX, in the north of Chile, and University of Concepcion, where we've been working on this for some time. Well, initially it was a lot of basic instrumentation, getting telescopes ready, doing site testing. Took us a long time, many young investigators who went through our hands. The actual observations, which was much more difficult than it looks, up at Apex. And it's, of course, it still is a large enough group. I only show the young investigators here. Engineers, master students, postdocs, a lot of people working on this here, concentrating only at Concepcion. And we're part of a larger thing called Titans, which is a nuclear millennium in Chile between Valparaiso, Santiago University, Chile, and us, with international collaborators all over, just showing a few of the key ones. So what was the point is that, again, as I mentioned, especially for this meeting, there are telescopes in Chile and there are telescopes in France, and so you'd imagine, okay, that's a collaboration. But I specifically marked it Chile, France, because in Chile it's ALMA and APEX, where we are users, but these are international telescopes that happen to be in Chile. With the NGHT Phase 1, a new telescope should come here to Chile, and this one we'll be actually managing ourselves. We've just finished writing the proposal. It gets submitted next week. Probably a $7 million investment of the total $100 million to come here. And so we'll actually operate, and that will then convert it to a Chilean-French baseline for sure, instead of just a Chile-France. And that's a lot of Inria, right? Changing Chile-France into Chilean-French. We have a lot of collaboration with scientists in France in general, especially through the EHT. What happens is just a Fourier transform plane that with these new telescopes, we just take more of the Fourier plane. Therefore, our imaging gets better. We have a Phase 2, which goes up. SPX, unfortunately, is not in France. It's in Switzerland, very close by, because we've run out of high mountains in France with good dry skies. And it just gets better and better. And in terms of frequency and angular resolution, you might see some names used. So NOEMA is in France, ALMA in Chile, JWST is up in space, and that red box is what we are aiming for. It doesn't matter what frequency, what resolution, just as high angular resolution and a frequency that nobody else has. So it's discovery space. There's a lot of science here that's quite across many fields. because really what we're doing is gravity. This is not exotic astronomy for astronomers. It's fundamental physics, gravity, frame dragging, testing, high-energy particle physics, binary black holes, photon rings, dynamics, all sorts of stuff. So what are we specifically doing? I showed you what's really expected with the NGHT is very nice. What this means is those ugly little images that we showed you already become movies. Every minute we can make a movie. So what we'll see here is actually gas swirling around the black hole, minute by minute, and I don't know doing what. Maybe falling in, maybe staying stable. We'll have to see. Maybe it just slows down as it gets closer to the horizon, but we'll actually see movies. What we're interested in is instead is to do demographics. So of course the NGHT is a big group, the HT is a big group. Now talking only about Titans. We collaborate with all of them, but we lead very specific projects. And our lead is in demographics. In the near future, we want to, instead of 2, we want to get about 8, and in the longer term future, hundreds of black hole shadows. Why? I mean, there's this typical joke, right? Aliens visit the Earth, they want to know all about humans. They interview 2 people, Bill Gates and Elon Musk, and they don't have more time, and they just go back and say, the whole of the Earth is like that, all humans. We can't do our physics and we can't do our fundamental physics with these 2 black holes. We need demographics to really understand not only the black hole and GR, but also the material that falls in, how does it fall in, why does it fall in, and how it gets shot out. We already know there's a huge diversity, we want to understand why. The problem is that you need something that's bright enough and large enough to be resolved, right? And so just making a diagram like this just took us about 10 years. It sounds trivial. You want to know how big the ring is, which means how massive the black hole is. More massive black holes have a more massive ring, plus they have to be close by. And how bright it is. There's no such thing as a survey at 250, 230 gigahertz. You do a lot of modeling of the spectral energy density of accretion flows and jets, and bid it down, and many, many master students later, you get what we have in purple, which is the gold sample, which is what we're doing right now. We're actually observing the first few. They're coming out really, really well, but we don't have results yet to show. But looking at that red cross, which is a hypothetical object, and what it should look like with next year when our data is fully ready, you see very little difference if a black hole is spinning or it's not spinning. If a black hole is spinning, it drags the magnetic field with it, and those blue arrows is what we can measure from the polarization, is the magnetic field. And there's a difference between low-spin black holes and high-spin black holes, plus there's a shadow in the middle, plus there's a lot of details. For example, right now we believe in SANE, in MAD models, magnetically arrested accretion disks, rather than the inverse, SANE. Without getting into the details, you do a lot of particle physics here. So this is our big point, is like 2024 onwards, we're going to start our first demographics, because these are long-term projects. And we want to follow all of these purple ones. The others, actually, there are 3 million points. Most of them are here, here, and here. Of those 3 million, it's looking for needles in a haystack. We have about 25 that we settle down with. We also want to do binary black holes. These are 2 supermassive black holes falling into each other. They emit gravitational waves. We found gravitational waves from stellar mass black holes falling into each other, but not from supermassive. There will be a project ELISA, or LISA, which will fly in space, which is very similar to LIGO, but just on very long baselines, and that'll be stable enough to look for supermassive black hole binaries. There are pulsar timing arrays that are trying to do it. Here at Titans and UREC, we're trying to race against them, and we hope to, not because we can image them. We don't have to look for the gravitational waves. We could actually image 2 black holes orbiting each other and falling into each other. And that's what we're trying to do. Very high risk, but let's see. So far, we have promising results in our preliminary searches. So once more, just to say, without really looking at the graph, that's the linear resolution that the EHT has across the universe. It's very, very fine, the resolution. It's reading a newspaper in Paris from here, if the newspaper is bright enough. And so with that, you can see sub-parsec resolution, whatever that means, all across the universe. What it means really is this sub-parsec regime is where binary black holes start to emit gravitational waves. So we have a lot of candidates that we're kind of looking for them already. We have some in the disciplinary area. One is just the telescope operations, which sounds like just turn on a telescope and run it. It's actually quite complicated, and we're contributing to the instrumentation in it and everything. We're also doing a lot of site testing, because we need very dry sites for a radio telescope, and that's very interesting because we use MERA too. We use NASA reanalysis databases that look down and give you water vapor. Instead, our observatories have these very expensive radiometers looking up. And the ones looking down don't work well against ice, snow and ice, because there are certain problems. The one looking up, yes, they do work. And in fact, we have this big problem in our natural databases, NASA databases. You don't have the poles included because water vapor doesn't work. Their radiometers don't work. They typically black them out, or they put in values that are highly uncertain. When we are on the ground and it snows at our telescopes, we can measure upwards and we can calibrate them. So now we've started to find 10% differences, unfortunately in a bad sense. It looks like NASA databases are underestimating water vapor in the atmosphere by 10% over ice. But it's still preliminary results, but we want to measure this. Because remember, water vapor is the largest global warming gas, effectively. We talk about CO2 because that's what we produce. But water vapor has a larger effect. It's just a byproduct of the heat that we've already dumped in. And we also need satellite communication from Antarctica because we're going to record at 300 gigabits per second. And we need to get some of that data out. Otherwise, it stays on a disk frozen in Antarctica for 6 months or 9 months before it can be flown out. A lot of our technology work is done here at SEPIA, which is the radio astronomy laboratory. And so basically what it's really about is fundamental physics, very high temperature plasmas, ejections at relativistic velocities, and binary supermassive black holes, and doing demographics out of this. And I leave that up there. We have a very active outreach program that we're very proud about, annual events, typical topical events, and we plan to continue this.
Well, thank you very much. Stay there that we have some questions, probably. Go ahead.
Neil, how do you estimate the mass of the black holes?
So it depends on which one you want to do first. So we first wanted to test general relativity. So we wanted an a priori mass. So we took the mass of Sagittarius stars well known from orbits around the black hole. And M87, it's also from stellar kinematics. So we took the previously measured masses and then tested GR. And our result was GR, because our images, they'll get much better. We should get to 1% tests. We are now at 18%, 1.8. Because our images are low enough resolution, we're not quite sure. You remember the ring is supposed to be a fine ring, and we see this very fat donut. We're not quite sure where the ring is within that fat donut. So we got to 18%. But if you turn the argument around and you say GR is correct, then you can measure the black hole. Then the ring, if GR is perfectly correct, then the size of the ring is 10.4 times the RG, the gravitational radius. And this, for example, will give you a black hole mass for each one of them, which is relatively the same. What do you think is more important? Trust GR and go for black hole mass, or take a priori black hole mass and test GR?
No, black hole mass first.
Okay, well, that's what we're doing now, and we'll continue for some time. And we're hoping it'll break down, right? And that would be very interesting if we find something that is not right with GR. It always wins so far.
Any more questions? This is I would spend hours asking, any nerd on Earth wants to learn about this. So, but we are running out of time. Thank you very much.
Thanks a lot.
It's a very interesting topic. Theo. Last but not least, we have Theo Signor. Theo is currently a PhD candidate in astrophysics at the University Diego Portales and in Inria, Chile. He's co-directed by NIAD. He holds a master's degree in data science for physics and a bachelor degree in astronomy, both obtained at the University of Padua. And Theo's research spans the application of machine learning to the study of distant galaxies and the optimization of the representation of GPS space vehicles orbits. His PhDs focus on modeling stellar atmospheres. I have to say, Neil is a very good example for Theo, except for the time of doing the PhD thesis. Thanks. Go ahead.
Hi. Thank you for the presentation, for the introduction. Yeah, we had like a couple of very interesting talks now. It's intimidating. Okay, so today I'm going to talk about one of the projects related to astronomy that we are working on now at Inria, Chile, in collaboration with Diego Portales University. And this is about developing an automated way to find, to identify and suggest candidate stars from disrupted dwarf galaxies using low-resolution spectroscopy. So this is a work in progress. We recently started working on it. So I'm gonna focus on the scientific motivations behind it, the approach we are taking to solve it, and the very preliminary results we have today. I was hoping to have better results, but we will have to wait probably 1 month to have nicer results. But we are going to discuss about the preliminaries, and I will also touch briefly on the other projects that are related to this one. So, okay. I will describe what every word in the title means, starting from the what is a galaxy, because I've learned not to take for granted this. So the simple explanation is it's just an ensemble of stars, gas, planets, black holes, dark energy and dark matter held together by gravitational forces. Here we have two pretty images. One is probably Andromeda, and the other is a artistic representation of the Milky Way. So these are two relative, not small galaxies. But so what happens if a small galaxy, which we call dwarf galaxy, is living nearby to one to a bigger one? So here we have an example of like a simulation of what happened to the Sagittarius dwarf galaxies, which was orbiting, not orbiting, but was living nearby to the Milky Way, that we can see in cosmic times get attracted by the gravitational pull of the Milky Way and get literally eaten by the Milky Way. So you can think about like a dwarf galaxy, like a ball of little balls, and these little balls are the stars. And when they interact with the Milky Way gravitational potential, these little balls get dispersed, and they get, and so these galaxies get destroyed and cannibalized by the bigger galaxy. And the stars belonging to these dwarf galaxies become part of this stellar population. And billions of years ago, the proto-Milky Way was surrounded by a lot of these dwarf galaxies. But as I said, the majority of these are disrupted by the Milky Way gravitational potential. But studying this system and understanding this system is important to understand the history of formation of the Milky Way. And this is a branch of the field called galactic archaeology. I don't know if you ever heard of this. So how do we study these disrupted systems if they are disrupted? By using their chemistry. Okay, a star star get created by the gravitational collapse of clouds of gas and dust. So this nebula, star-forming nebula, contracts, and in this are produced multiple stars. And so the chemical abundances at the surface of the star resemble the chemical composition of the environment in which they form. So we use this feature, this characteristic of the chemical abundances in the atmospheres as a sort of DNA. So we use the chemical abundances are DNA traits. Like here we have a previous project that we're working on, and it's in preparation. I hope I have the paper soon, where we try a supervised approach to set a baseline on the relationship between chemical abundances and birthplaces for stars that are born in the Milky Way. And you can see that, okay, the mapping is not perfect, but there is a good amount of information about the birthplace contained in the chemistry of the star. And we can also add a temporal dimension here, because you can see that stars, during their lifetimes, they produce and synthesize new elements. And when the star dies, gives back these newly created elements to the interstellar medium. And from this interstellar medium, I created new stars. So as you can see, you can think about this as a sort of inheritance. And here we have a project that we are working on in the Nuclear Millennium Ares, which I'm part of, and Inria is a collaborator, where we are trying to reconstruct the history of formation of the Milky Way by using evolutionary tree, which are a biology tool commonly used to reconstruct the evolutionary history of living species. So, going back to the dwarf galaxies, these galaxies have are different. They have a different efficiency in the production of stars compared to the bigger galaxies. So they have a different star formation history, different given the difference initial mass function. So they have different chemical signatures. So it is in theory possible to recover this disrupted system by studying their chemical abundances at their surface. In particular, we expect these stars to be what we say alpha poor, metal poor. There are the alpha chemical elements and the metallicity, in this case the iron, where we can see in this plot here where the vast majority of the star observed, every point corresponds to a star, are from the Milky Way. And in the bottom left panel here, highlighted here, we expect to find, it's the parameter space where we expect to find this this star from disrupted dwarf galaxies. And we expect SDSS-5 to observe thousands of these stars. This is currently a running survey. There are some internal data products, but so this is happening right now. So first I have to do a little digression on how do we measure chemical abundances of stars by studying their stellar spectrum. The spectrum is like flux as function of wavelength. So you know that the light is created at the inner layers of the star, and then on the outer layers, there are the absorbed species that absorb the light, and every one of these species, according to what they are and the atmospheric condition, absorb in different ways. Like so, the spectra of the star is globally a black body, but you see those lines, if we zoom in, every one of these lines can tell us information about the different elements, and also the general spectra that can tell us other atmospheric parameters like temperature and surface gravity. So what is currently happening now is that since a couple of years, we have been obtaining low resolution spectroscopy for stars in the galactic halo, where we expect to find most of these galaxies. But obtaining reliable abundance estimate for this star is not that trivial, and it's expensive. So you say, okay, you take the spectra, you feed the spectrum to some theoretical template, and with this you can infer the chemical abundances. And also, in particular, in this metallicity range, you cannot, at least at the best of my knowledge, use the classical, synthetic spectra fitting template, because of the uncertainty provided by the theoretical models that are employed to synthesize these kind of stars. Because, stars are commonly modeled as 1D objects, and we found that when we model stars as 1D objects, especially at low metallicity, you can have biases in the predicted abundances at surface temperature. And this is also another project that we are working on at Inria to improve the modeling of this kind of stars using a physics-informed learning. But this, I think I will talk about it next year. So, overall, summarizing, we need a tool to quickly identify and suggest interesting objects. And this is the goal of this project, so to develop an automated way to suggest candidates, exploring the large dataset that we have with SDSS-5 using low-resolution spectra. And we recasted this problem as an anomaly detection problem, because not a classification problem, because we don't really have data to train a classifier, at least today. So we just want to find anomalies in the chemical space starting from spectra, and in an unsupervised way. So the only thing we know about is the observation, the spectra. And this is our pipeline. So given that we don't even have yet a validation set for this kind of stars, as other astronomers and other collaborators are collecting data, but today we don't have like even a validation set, a big enough validation set. So we start from simulation. We synthesize spectra with given atmospheric parameters that we expect to observe with BOS. And with this, we can elaborate, we can develop our anomaly detection algorithm and also validate them. And after this, we plan to do it on real data, clearly. So first test is to run classical anomaly detection algorithms starting from spectra, like isolation forest and one class support vector machine. And guess what? It doesn't work. Clearly, like as you can see here, we have the predicted anomalies and the predicted normal stars, and you can see that they are not in the bottom left region of the diagram as we wish. But this was kind of expected, and it is not working in a good way because we are finding anomalies in temperature instead than chemistry. But why? Because temperature is the parameter that probably most affects the spectrum. So what do we do? If classical algorithms don't work, you go to deep learning. So we aim to change the representation of the spectra by using an autoencoder-based architecture where we just train this autoencoder to reconstruct its input, which is the spectra. And in this case, a spectrum is composed by like 2,000 or more features. And we know that we don't need all these features. It has been shown that you need very, very little features to describe completely a spectrum, like probably less than 20. And, but also, if you use like a normal, like a convolutional variational autoencoder, still, also the latent space Z, which is the layer which contains the minimum information you need to describe a spectra, is mostly like here we have the mutual information score, and Z1 to Z4 are the latent features, are mostly related to the temperature and the surface gravity, but we don't care about that. So we need to find a representation space which is independent on these parameters. So how do we do that? With disentangled representation learning, and this is what we are running now. So see, we don't have results for this, but this is our approach. So we still keep the encoder-decoder architecture. So we have an autoencoder trained to reconstruct its input, but at the latent space Z, we append a classifier which has the goal to predict the nuisance parameter, which are the temperature and surface gravity, the parameters we don't care about. So, and the encoder, so this classifier is trained to predict those, but the encoder, the goal of the encoder also now is to make the task of the classifier impossible. So convergence is reached when the performance of the classifier is comparable to the one of a random classifier or a dummy classifier. So I say here, these are very preliminary results. We're running it now. So the convergence is not achieved yet, but I just show you what we expect. Like here you see we greatly reduced in this way, clearly, the dependence of the latent space on temperature and log G. And so we then find anomalies in metallicity. Metallicity plus a bit of log G, because I said the convergence is not reached yet. So, but this is just very preliminary thing. Things improved, but I think that in a month, like very soon, we will have much better results. We're running these things now. So I wrap up here. So like when this convergence will be reached for the previous architecture that I was showing, we hope to have a latent space which depends only on the chemistry, or mostly on chemistry, because we want to find anomalies in chemistry. So we want to deliver an automated method to hunt stars from disrupted dwarf galaxies, starting from low resolution spectroscopy and noisy spectroscopy. So thank you.
Thank you very much. Questions?
So, when you mean the reconstructed so, when you mean the reconstructed spectrum, how-
Yeah,
so the reconstructed spectrum,
like here, for example.
yeah, that one.
Yeah, okay, an autoencoder is a kind of neural network.
Yeah.
Ah, no, sorry, I thought you
Yeah,
finished.
no. I mean,
Sorry.
reconstructed spectrum. How should be? I mean, what should be the differences between the reconstructed and the original spectrum?
Noise.
So it's okay. So it's a less noisy version or a noisier version
Yeah,
of the original one.
it should be a less noisy.
A less noisy.
Yes.
Okay. So you remove the effects of temperature and surface gravity, but then
In this
Yeah.
case here, like as you see, we provide to the decoder the temperature and the surface gravity.
okay.
So we reconstruct using the latent space plus those.
Ah, right. So you in the reconstructed spectrum, you already know what are the temperature and the surface gravity.
Yes.
Okay, and then what is undetermined is are the abundances.
Yes.
Okay.
Yeah, because temperature and surface gravity are easier to estimate than the chemical abundances.
Right. And this is star by star.
Yes.
Okay.
Yes. So we want for every star to find a representation space that is dependent only on chemistry.
Okay. Thank you.
Yeah. Sorry if I interrupted. Is that I thought you finished. Sí.
So thanks for the presentation. I think the obvious question is, what library are you using for computing your outlier detections?
Scalar.
So usually I would think that preprocessing is quite important, and seeing that it's mostly the temperature that is being, yeah, I see normalizing missing data. Okay.
But it is not normalized like in a standard scale, like a standard scale or minima scale. It's not doing like feature-wise, but it is doing to normalize the continuum. So like exactly, you see that we have a curve, and we flatten it essentially. That's the normalization we mean. It's called continuum normalization, and that's done with an S-spline.
Okay, splines. That's already interesting. Okay, I think we should discuss afterwards. Thanks.
Thank you very much to everyone, to all the speakers and our chair, Luis Martí. Now I want to invite you really fast, because of before of the coffee, because we're late, to all of you to come here to the stage so we can take a group picture. Thank you very much. So we have a good memory. I love it. What a great idea. Pero tal vez
no quiere estar adelante.
Menos peor. Más.
La persona que está detrás de Luis Martí. La persona que está detrás tuyo, Luis, que no se ve nada de nada de nada.
Está en la mitad. Menos de unos 60.
Usted. Sí. Sí. No, no, él igual no quiere salir mucho, así que está bien. Ay, sí, perfecto, muchas gracias. Sí. So, if you can, if you try to be in the middle of two people, if you are in the back line, so.
Aquí si quieres. Falta. Inria. Saltando. Volando. Ve. Saltando, pues.
Muchas gracias. Volvemos a la sala en 10 minutos, así que agradeceremos la puntualidad. Sí, rápido.
tengo que ponerme aquí y aquí se escucha. Ya sí, salió recién. Claro, porque si no se van a tener que estar pasando todo el rato. Sí, porque yo me imagino que van a ir.
Welcome back, everyone. Thank you for your punctuality. I hope you have enjoyed the coffee break. Now we proceed to the round table, challenges and opportunities in the Bio region, which will be moderated by Nayat Sanchez-P.
Yeah, hello everyone. Good afternoon. Thank you for being here after the coffee. I hope you had coffee so we can stay a little bit more to finish these 2 slots that we have still before us. So thank you so much. So I'm moderating a panel, Challenges and Opportunities in Bio. Well, in the program of the Scientific Days, together with the Scientific Committee, we have insisted a lot in including this space of debates with the idea of trying to promote the opportunities of each region together with the private sector in one sense, and the other one we were discussing about enabling factors in Chile for AI. But the opportunity of coming to region is also an opportunity to discuss the challenges and also the opportunities to connect, right, on top of that. So to discuss this, we have the honor to count with the presence of distinguished panelists. In the first place, we will have Sofia Valenzuela, the Science, Technology, Knowledge and Innovation Regional Ministerial Secretary. Please, Sofia, come to the stage. Thank you for being here. Guillermo Cabrera, the Director of the Universidad de Concepción of the Doctoral Program of AI. You already heard the fantastic keynotes that Guillermo just gave, and Pablo Aquebeque, Director of the Center of Industry 4.0. We will have just only 30 minutes to discuss. Yeah, it seems that we privilege the coffee, yeah, in this late afternoon. But and I will do my best to keep the time because Sofia needs to leave for another meeting. Okay, so. Well, thank you so much for agreeing, first of all, to take part of this discussion. And Sofia, I wanted to start with you because in France we have like decentralized, I would say, republic by constitution, which means that the regions has autonomy, right? And define their local strategies and so on. And it seems that in France we are moving even more to an autonomous management, even in the research management model. Okay, so the government of Bio, I understand that you have a regional strategy for development and also a regional strategy that is connected to science, right? Can you tell us a little bit which are the main emphases of this strategy and how it is connected to science and the Minister of Science, and how do you see the collaboration of the universities, for example, and the research institutions inside of that?
Yes. Thank you. Good afternoon, everybody. Yes, in our case, in the region of Bio, and each region of our country is developing strategy in science, technology, knowledge, and innovation. So we have all 4 pillars. In the case of Bio, the strategy is already developed. We have to approve it, probably next week or the following week. But it seems it's going to be approved by the Committee of Science Technology. And it includes lots of things that need to be done. In first place, it acknowledges all the strengths that we have in research and development as the ecosystem of universities, probably some startups or spin-offs that are currently located in our region. But at the same time, it also tells that we need to have more investment from the private sector and R&D. That is one of the things that has to be done, as well as to develop more people or PhDs probably or master's degree in different areas, and sit in the morning to retain them here, to keep them here. That is one of the main tasks that we have detected, that most of the people that are get their PhDs, their master degrees, or professional training within the region, they just leave. We have to make Bio attractive for innovation. That's one of our challenges.
Do we have another mic, second mic or not? So with respect to that, I have another question because, yeah, effectively, you during the inauguration, I mean, you said a couple of words that you have a strategy as a Minister of Science of retaining in the region the people. Have you thought in any specific program to attract researchers to stay in the? I mean, how you envision that?
Sorry. During the post-pandemic, or during the pandemic, we saw that many people that were in Santiago migrated to different regions of our country. Despite that, not many people came to Biobío. They did go probably to the south of Chile, Valdivia, and that sector, Los Rios, which is nice. It has lots of lakes and things like that. But in Biobío, we didn't see an increase of people coming to Biobío. I would think that one of the things we need to do and work together with the universities is to, for example, create new startups or spin-offs based on science and technology, not only in Concepcion, because that's another problem that we have. All of the investment of our ministry and most of the investment in science and technology or research and development is in Concepcion, one city. And we have 33 comunas within Biobío. So we have to do decentralization is one major task. And I think that with people that are finishing their programs, PhD programs, for example, in artificial intelligence, can be one of the things that we can do by investing in their thesis work and relate that with some productive sectors, not only in Concepcion, but with surroundings of Concepcion, so they can go and develop some strategies or some solutions for the productive sector, and then they can be hired by these same companies. And as well to attract foreign people, that is another challenge. Universities have done kind of well, I would say. And we, as ministry, we also have some instruments as postdoc programs that allow to people to come into the country for 3 years, almost financed by, or fully financed by the Ministry of Science. And that is one instrument that is not very well used for foreign students. It is well used by Chilean students. And there's another instrument that I would say universities can use, but also companies can use, which is the insertion of postdocs in universities or the productive sector. In that case, we also have the possibility of people from other countries to come here and insert their and start to work in the Biobío region. But again, not many people use this instrument. I don't know if because they don't know it or because Biobío is not so attractive, but we need to do. This means also within the strategy of the region is to develop a little bit more the tourism within the region. I think that could be attractive, but we still need to attract people, and it's challenging. I think there's not only one solution for that. It's very complex.
Yeah, imagine complex and challenging, and even more if you want to promote international collaboration. Because I mean, if you want to be that, if you want to put the Biobío region, I mean, in the map of the world, you need to attract and have really instruments to attract not only postdocs but also researchers that train those postdocs, etc. So Guillermo, I want to jump to you because you are right now. You just congratulations, because you just you are the director for the Universidad de Concepción of this PhD of AI, which is the first PhD of AI of Chile, right? And this is, as far as I know, it was a very challenging program, to be built, because you have a consortium of 4 universities. Can you tell us a little bit about the characteristics of the program and how you see that this program could eventually take advantage of the international collaboration?
Yeah, thank you. So yes, we built this program. It started as an idea for like initiative for AI within the university, but the president, the rector of the university, what he did was that he extended this idea to other 3 universities, and those are the Universidad Católica de la Santísima Concepción, Santa María, and University of Bio Bio, right? And so the rectors decided to build this program. And right now, the program is hosted by the 4 universities. So, for example, I am the director for the program for the University of Concepción, but there's another director at Santa Maria and another director at UBB and so on and so forth. And it's super important that when a student goes into the program, he's a student from all 4 universities. And once he graduates from 4 universities. So the grade, it's going to be signed by the 4 presidents of the university. And in terms of, so it has been really challenging, I have to be honest. We started building the program like 2 years ago. And it's challenging because each university sees a PhD program from their own perspective. So trying to combine all of them into one single program, it's challenging, right? So we're funded by the government, the local government from the BOBO. And the other thing that's important is that we're constantly, so it's super important for us that the program makes a huge impact in the region. Okay, that's the major goal. So the way we're thinking about this is we're attracting people to the region. So that's really important, attracting talent. At the same time, creating and forming talent from local people here in the region, right? But what I think it's going to be tough, that it's not a problem right now, but it's going to be a problem maybe in 4 years, is that we want to keep them here. So this is something that happened in Canada. I'm not sure if you know, but Canada is like where AI grew faster in the world and where they have the Turing Awards and stuff like that. And at some point, what happened in Canada is that people went to Canada, they took their PhD programs, and then they left for Google or Amazon or Meta nowadays or whatever, right? So what they did in Canada, which was super important, and I think that it's something that we should try to imitate, is that at some point, the universities met with the public sector and with the government, and they decided to create a program to keep the experts in AI in Canada. So they built 3 major research centers in artificial intelligence in different places in Canada. And now, and those centers do basic research, they do applied research, and they also do technology transfer to the industry. So it's like they build the whole chain of knowledge. And the way they work is that they have a board with people from the private and public sectors. Thanks. And the board says these are going to be the challenges for the next 5 years, right? And that goes all the way up to the researchers, and the researchers start doing applied and fundamental research in AI for those challenges, and they get funded by these centers. So I think that something like that could work like really nice here in Concepcion, but we need to all agree that we should do something like this. And I think that it's kind of obvious, but at the same time it's challenging again, because you need to put the 3 areas, the 3 sectors into the same table and say, we're going to do this, and we're going to be the major impulsor of AI in the region.
And this is a multi-stakeholder conversation. Everything around AI is like that, right? So, and I think that there's a lot of challenges. I mean, Chile right now is trying to position itself as a regional, leader of AI in Latin America. So I think it's a very good opportunity right now that you have a structure, something like that could be connected with the strategy, the local strategy, or regional strategy that you have here in the region of Bio Bio, and probably this input with respect to the lines, strategic lines of priorities that you will have as a region, and also with respect aligned with the Ministry of Science, could be a very nice input also to consolidate something like that, and also to provide example to the private sector that we need them to invest a little bit more in science. Pablo, you are the director of a center that is more connected to the private sector, right? Because this is the Center for Industry 4.0, right? So, and considering the rapid advances that we are living today with respect to technology, mainly with AI, etc., what do you think are the most pressing, challenges that you're facing, and that could make a substantial impact in the region? What do you say?
Oh, I think the big challenge is to push to the companies to acquire the technology, to acquire the knowledge for apply the different tools for the AI to different process. And I think we have a very big difference between the very big companies and the medium and small size companies, because the last one are very later from the technology advances, are very, and we are pushing to, I think, in a digital transformation. It's very late for that companies, and they see they are very bad to the new technology appliance to the process, for example, and it's not easy to they understand how we can and they can apply for this industrial process. The very big companies put a lot of money to do some research project and apply to different process. For example, here, Guillermo is working a lot with different companies, but this is a very different from the very big companies and medium and small size. And I think we need to do a platform to push that companies, and it's an opportunity as well to do the platform with the people from the different AI studies here.
And we'll do a last round. We have 10 minutes, but I'm taking care of the time, right? I'm just a good police, okay? I would just get another round of questions with respect to collaboration, international collaboration, because this event has to do everything with collaboration, right? And the proof that we want to collaborate with the region is that 15 researchers from France are here, are traveling, and we have organized all of this and made this scientific caravan for 4 days, trying to approach and to bring friends to Chile. And then I want to hear, and probably that you say some words, how you see that we can connect France and Chile, the region of Biobío and France, through Inria, and probably in some priorities that you could see, I don't know, for example, Sofia.
Yes, I think the region of Biobío is very active in trying to have new networks. There are a couple of examples of projects that have been financed by the regional government. As we said before, the Smart City project here at Concepcion that is in collaboration with MIT. And I think there's a good connection that we could make there in digital sciences. There are many small, medium enterprises within the region, mainly at Concepcion, that, as Pablo was saying, need to get more digital sciences into their processes, into their services. I think that could be one opportunity also, not only with universities, but going through the productive sector. Because as I said before, in our country, the investment in science and technology is not as high as we would like it to be. It is increasing. But we have a major debt in the countries that 80% of the budget that goes into R&D comes from the state or the government. Only 20% from the private sector. And 20% that includes when they change any device or anything. So it's not really that 20%. And I would say that in-house research is very little. There are only a few companies that do in-house research. So there's a good opportunity for Inria and internalization, not only with universities, but also with the productive sector. So they can start doing, in collaboration with universities, R&D, and start to do their own R&D, which is a way also to attract and retain the people that we are forming within the Biobío region.
Yes, I was thinking while you were talking about how to do this connection, and Actually, I think that there's something that you said that's important, that we already have some connections. So we kind of know how to make these connections. And usually the way this works is that you have a colleague from University of Concepcion and a colleague from the US or from Germany or the UK. I'm not mentioning France yet. I'm gonna talk about France. Yeah. And you have a colleague in which, in a topic that you work together, and you usually co-fund students from both universities. And the good thing is that we here, at least at University of Concepcion, we have really good students. And colleagues from other universities asked us for students. So for example, I have 2 students right now at Harvard. I mentioned one of them before. We have international programs with Heidelberg. You have with Oxford, right? Yeah. So in general, we do make these things happen. Now, in terms of this kind of events, they are super good to know what other researchers are doing from France, for example. I don't have a strong connection with France because I've never been exposed to what researchers in France. Except for today, exactly. Exactly, except for today. So these kind of events are really good for that. If you can make the connection, right? Because, for example, if someone asked me to start working on oceanography, sorry about the oceanographers here, it's not my field, so I wouldn't feel comfortable just jumping into a new field. But if I find someone that works on something similar than I do, then it's like trivial, right? We can trivially collaborate with that, and we can fund 2 students. That's not that hard, right? Not for us, maybe, and most likely not for France. And if we do that, we make the connection, right? And then we do internships and stuff like that.
Yeah, in my point of view, the international collaboration from the university with overseas is very good, but we have the challenge to conduct a relationship with the companies here. Because for research projects, it's very good for us. We have some very good researchers, but always it's necessary to transfer that research project and apply research projects to the companies here. And always we are thinking how we can do that. It's not easy because, how I say you, the small companies, they are not prepared. They have a very low technology level. They need to digital transformation. And for medium-sized and very big companies, it's more easy across that researcher that they are working with the companies there. I think that is the opportunity to transfer from research, international research project with the companies here.
Yeah, great. And well, first, thank you so much to 3 of you. I just want to say that the next slot that I want you to stay just to listen, because answers somehow, the solutions that you are providing here, because we are now presenting the cooperation programs and the instruments that we have to fund that normally we do. The things that you just already mentioned, we have an internship program. Together, every year we send 15 students to France, and they are connected to a research team, and they do research stays for 3 months. And this ended up connecting also the research, the supervisors, right? So there's a project that is being done, etc. Also, we have, I won't do a spoiler of the next session, but they will be presented all of that, but also we have programs to connect researchers in terms of the basic science, but also applied science. We have all of that. And well, again, thank you so much. We're very interested in connecting with the Bio region, and I hope we can do our best to connect on that. So I will let then the floor. First, thank you to the panelists. And I want to let the floor right now to Cecile is here? Okay. I thought you were not. To Cecile Vigoureau and to Luis, that will be presenting the program of cooperation and also the Inria French-Chilean network of researchers that we launched last year, and we invite you all to get involved.
Okay, thank you. Magic, you mean? Okay.
You just need to visualize your slides.
Yeah. Yeah, we see the magic happening actually, but so. Yeah. Okay. So thank you, Nayat, for giving us the floor. So as Nayat mentioned, we are going to focus on two topics. First of all, the French-Chilean network for researchers, since for more than 11 years of the existence with Inria Chile, there have been a lot of collaboration. There were, of course, already informal collaboration. I will come back to that in 1 second. There were informal collaboration existing before Inria Chile, but creating Inria Chile allowed to put a lot of collaboration, I would say, on the map with more visibility, and also giving, helping to establish reputation for Inria in Chile on one side and Chilean University in France on the other side. And I would like to come back to the thing that were mentioned about the internship. Where are you, Guillermo? Oh, there, yeah. So you mentioned, okay, so you mentioned, and I totally agree with you, that you can do internship with your colleague and have one student and exchange. But what we built through the internship program of Inria Chile, as Nayat mentioned, we have 15 students each year coming at Inria, and I think the colleagues from Inria in the room can vouch for the fact that having students, excellent students each year, gives information about the university, and not only to the researcher that is receiving the student, but also to this colleague. To be able to have not only single exchange, but more visible programs with yearly code, and be able to expand it, as we hope to do here in Concepcion, University of Concepcion, is really important. And the same goes with researchers. Having programs that we are going to present now that are run every year, not once, but really every year, and of course the laureate will change, is really something that helps giving the collaboration visibility, and visibility on a political level, because then when there are some discussion between France and Chile to discuss about what are the topics we want to push forward and what are the topics we want to put money in, this is important when you can show that you have already structured mobility programs, or as Louise will also detail, also collaborative projects. So that's why we can only do that if we have a network of French and Chilean researchers that know each other, that help their colleagues discover their colleagues, like making the network grow. And this network has been existing for a long time informally, but now we really want to have something that can be put on the map of the collaboration between Inria and Chile, and between France and Chile. And so we are really open to any suggestion of developing this network. And now I leave the floor to Luis. Thank you. You can do it in Spanish, actually.
Yes. Spanish? English? Oh, vale.
Así.
Vale, así voy más rápido. Esto cambia solo. Bueno, muchas gracias. Aquí de nuevo. Como les comentó Cecilia antes, hemos creado esta red franco-chilena de investigadores de Inria, ¿no? Y la idea es agrupar debajo de esta red, debajo de este paraguas, las diferentes acciones y actividades que tenemos en relación a esto, ¿no? Por supuesto, no solo, además de los programas, tenemos una diferente serie de acciones, de matchmaking, actividades como estas, para un poco irnos acercando y que, bueno, por otro lado, una forma sencilla de enterarse de lo que estamos haciendo es a través de las redes sociales. Entonces hay un grupo de acciones o de actividades que tiene esta red, y lo que voy a hacer es enumerar primero los programas que hay para poder, digamos, primero hablar de las herramientas y después un poco contarles de cómo usar estas herramientas, ¿no? La primera, este es un programa de Inria, o sea, con fondos de Inria, que Inria lo abre en realidad a todo el mundo. Se llaman los equipos asociados. Yo encuentro que es una idea muy interesante. Inria, no sé si saben, está agrupado en equipos de investigación de más o menos 20 o 30 personas en un tema muy particular, digamos Y entonces estos equipos asociados asocian a un equipo de Inria con un equipo de investigadores de fuera. Durante 3 años con un financiamiento de 36.000 euros, que bueno, no da para irse a Tahití, pero da para hacer algún tipo de actividad y encontrarse, empezar sobre todo a realizar una investigación conjunta, ¿no? Nosotros tenemos bastantes buenas experiencias en este sentido y de hecho aquí con Concepción hay varios equipos asociados, ¿no? El deadline para presentarlos es en octubre. Y si tienen alguna idea, o sea, por ejemplo, si les gustaría y a lo mejor han visto un equipo de Inria con quien les gustaría trabajar, ¿no? Por ejemplo, antes estábamos hablando de Camembert, del LLM este francés, que es de Benoît Sagot, que es de un equipo de Inria, de Almanac, ¿no? Pues si alguien quiere trabajar con esto, que se ha dicho de paso, trabajan en varios temas interesantes de procesamiento del lenguaje natural, pues por ejemplo, me pueden preguntar a mí, yo conozco a estas personas, tengo, digamos, una relación de amistad o de colegas, entonces, de alguna forma tengo este otro gorro de poder catalizar este tipo de actividad. Entonces, esto puede ser interesante, como anótense, ¿no? Más o menos en junio o julio salen las llamadas y se puede montar este tipo de proyectos, ¿no? Aquí tenemos las estadísticas. Perdónenme que me sorprende un poco las propias transparencias, pero bueno, tenemos ahora mismo, desde el 2012, 30 equipos asociados, ¿no? Y recientemente hemos tenido como un boom de este tipo con Chile, sí, con Chile. Los equipos asociados, de nuevo, es un programa de Inria que por supuesto tiene prioridades, entre las cuales está Chile, pero está abierto a todo el mundo. Después están estos Inria International Chairs, que están enfocados a investigadores, en que es un programa para que investigadores del mundo se pasen un cierto tiempo trabajando en Inria con un equipo de investigación de Inria. Y hay 2 escalas, 2 divisiones, una para investigadores más avanzados, con más de 5 años de experiencia, y una que esto es nuevo, si no recuerdo mal, for this year, the more junior line, is it's a new program for junior researchers to spend time in India. It doesn't have to be like 10 straight months. Across 5 years you can spend, lo siento, pueden pasarse 12 meses, ya es el 4º día, perdónenme. Y bueno, si de nuevo en el sitio web de Inria pueden visitar la lista de investigadores que han estado seleccionados antes. De nuevo encuentro que es un programa muy interesante. Y por otro lado tenemos estos puestos de postdocs que están, digamos, bajo el presupuesto de la Dirección de Relaciones Internacionales de Inria. Además de eso, bueno, otros equipos de Inria tienen llamadas a postdoc para sus proyectos, pero esto digamos, 2 plazas que tenemos reservadas cada año enfocadas a reforzar la colaboración con Chile, ¿no? Entonces, de nuevo, ahora mismo tenemos 2 postdocs y Katia, que presentó hoy, es nuestra conejillo de Indias, que está empezando su acaba de empezar. Entonces, bueno, esta es otra forma de articular esta colaboración, ¿no? En este caso sería un postdoc que está la mayor parte del tiempo en Francia, ¿no? Y después este programa de internship, que yo tengo que confesarles que me gusta mucho cómo funciona y lo hemos estado ejecutando en los últimos años y cada vez creo yo que con más eficacia. En este caso tenemos este programa en ejecución con 3 universidades, con la Universidad de Chile, la Católica de Chile y la Federico Santa María en Valparaíso, y cada año van 5 alumnos de cada uno de estas universidades a pasarse de 3 meses en Inria, en Francia, en un equipo de investigación. Y la verdad es que casi siempre funciona muy bien, porque tenemos muchos casos en que el alumno que va acaba haciendo después el doctorado, después de graduarse en Inria, o a través, como estaba comentando Naya antes, a través de que ha ido un alumno, pues los investigadores, no sé, el tutor o tutora del lado chileno entra en contacto con los investigadores de Francia. Entonces, de hecho, hemos tenido ahora en estas jornadas científicas alumnos que fueron interns de este programa, que ahora están haciendo el doctorado, que ahora han vuelto a Chile. Entonces, resulta una cosa muy interesante, ¿no? Después, todo esto es, digamos, un programa propio de Inria, que Inria tiene control completo de la cadena de decisión, digamos. Pero después hay varios programas externos relacionados de los cuales también nos podemos aprovechar. Uno es el programa ECOS, que estuvimos hablando antes, ¿no? Para la cooperación bilateral, está cofinanciado con la NIT. El deadline es alrededor de mayo. Y después están estos proyectos AMSUD, que tienen 3 direcciones. El AMSUD es la cooperación francesa con la América del Sur. Entonces hay un área relacionada con el clima y el cambio climático, una parte relacionada con matemáticas y otra con las tecnologías de la información. Y este es un proyecto, digamos, que tiene como un espíritu, o un tipo de proyecto que tiene un espíritu relativamente similar al equipo asociado. Es conectar varios equipos para que colaboren en 2 años y, digamos, creen unas primeras relaciones de trabajo, se puedan visitar y publiquen unos papers y estas cosas, ¿no? La verdad es que, bueno, en todos estos casos, aunque hemos tenido ejemplos de cómo hilvanando cada uno de los instrumentos, ¿no? Por ejemplo, nosotros hemos tenido un proyecto sobre cambio climático relacionado con Green AI, que después se convirtió en un equipo asociado, entonces hemos conseguido extender la cantidad de actividades que podemos hacer. O, por ejemplo, tenemos otro proyecto que es un Stick and Sud, que es un velero autónomo, junto con las universidades en Brasil y en Uruguay. Y entonces funcionó bien. Entonces el profesor en Francia, Philippe Preux, que no pudo estar hoy, pero vino a las jornadas científicas, se tuvo que volver hoy a Francia, encontró más fondos de sus fondos propios porque disfrutó y tenía muchos resultados interesantes y decidió financiar con fondos adicionales. Entonces, lo que me gusta de este tipo de acciones es que uno puede empezar a crear una sinergia, a lo mejor cada una independientemente, tratándola de forma aislada, es una acción un poco limitada, pero combinándola sin duda se pueden encontrar cosas interesantes. Yo creo que ese es el mensaje. Lo más importante es empezar a hacer algo, ¿no? Y empezar a encontrarlo. Por ejemplo, tengo que decir que el proyecto Stick and Sud del velero autónomo fue muy exitoso y muy conveniente porque del lado brasileño, mientras el resto de los países, incluyendo Francia, los fondos eran relativamente reducidos, Brasil pagaba por un postdoc full time. Entonces, esta persona fue en realidad quien, por supuesto, consiguió mover el proyecto porque había alguien que estaba dedicado y tenía, no sé, a 10 personas de jefe, pero conseguimos mover esto aquí. Entonces es interesante como entender estas herramientas y sobre todo decirles, bueno, se me olvidó comentarles que Claire, que también está aquí, se ha sentido enferma y no ha podido venir hoy, normalmente es quien les haría esta presentación mucho mejor que yo. Espero que se sienta bien si nos está mirando por el streaming. Si tienen alguna pregunta, alguna duda, no duden en acercársenos, ¿no? Se ha dicho de paso, ahora que lo pienso, nos falta un slide aquí porque también hay un programa de pasantías en Inria, Chile, ¿no? Este año hemos recibido 100 currículums. No sé cómo procesar nos hemos pasado con la difusión, pero que también es otra forma siempre es bueno encontrar como alguna forma, un punto de contacto en el que podamos colaborar y estas cosas, ¿está bien? Entonces, si tienen dudas, yo sé que he ido un poco rápido, aún más porque estoy hablando en español, no duden en escribirnos y preguntarnos, ¿está bien?
Y una última palabra, que en cualquier caso, bueno, efectivamente nosotros les vamos a enviar la presentación a través de la Perdón, que les vamos a enviar la presentación, perdón que hable en español para los colegas, que esta parte está más dirigida a los colegas acá. Y lo otro es que estamos trabajando con la Vicerrectoría Académica para establecer unos acuerdos más bilaterales con Inria también para el programa de pasantías y de movilidad de estudiantes y ojalá también para la movilidad de investigadores. ¿Vale? Eso.
Muchas gracias. Merci.
Questions? No? ¿Preguntas? Yes, one question.
I trusted you.
Thank you.
Sí, los programas de intercambio entonces son para estudiantes de pregrado.
Sí.
In English, please.
All right, yeah, so the internships are only for undergraduate students, right?
No.
No?
Master students.
Master students, okay. Right. PhD? No. Yeah, too.
It
All
could
right.
also be, there are
Yeah.
some laws that are currently changing in France, so for the time being we cannot have PhD with it, but there will be other schemes very soon. So
Right.
we
Yeah.
we have PhD. We can have PhD with this frame for the time being, and they will definitely still be in another.
Yeah,
frame.
I did an internship in France, and it wasn't easy.
Okay. And where did you do it?
At the Observatory of Paris.
Okay.
Yeah, it was nice, but I had to limit the time because there was.
That is why the internships are 3 months, by the way.
Yeah. Okay. Anyway, and for us, I mean, for researchers, senior or junior researchers, the option is to do to submit a joint research proposal, basically.
Yeah, for if you want to have this associated team or the stick and suit, no, you get in touch if you want with us and organize an associated team, 2 teams working together, no.
Okay.
And the proposal is really, really compact. You don't need to write a lot of things. And I can give you some advice.
Okay. Yeah. Right.
And actually, if I may compliment, so you have 2 ways. You have the way for the if you want to go through if you want to go to the collaborative project, then it's definitely associate team or AMSUD, but you have also the individual mobility with the international chair. And in that case, you choose when you come alone, so to speak, it's only for the laureate. You visit Inria, and each time you are in Inria, you are paid by Inria.
Okay.
According to your level of experience. So it depends the way you want to build your collaboration. And you can do one and then another one, of course. It's not exclusive. You can add the mobilities, but there are different ways of coming.
Thank you.
That is what I was meaning before, that is additive, no? So you can just start piling up things.
And the spirit of the program, just to add, I just will hand it to you, but the spirit of those programs is try to combine the DNA of Inria in the way they work, okay? Because the structure, in the way it is structured, the research at Inria is because of the project teams, right? So the idea of these programs, of the associated teams and other, is try to construct and to build like a bilateral, I would say, teams, okay, between French and Chile. This is why the network is French and Chile, okay, in the same spirit, right? So with the research projects, I mean, with the objectives and all of that is reviewed with Scientific. Guillermo.
Thank you. So regarding this internship program for students, do they need to apply, or do their application have to be within an already existing collaboration between someone at University of Concepcion and someone in France?
I'll let you explain.
Nayat is saying
Okay,
no.
then I can
No,
make it.
but let Nayat, because I think she...
And so, somebody else. Yeah.
No más departamentos de la universidad quisieron inscribirse en ese programa cuando las autoridades de INSA ese era el tipo de pregunta. Inria no tiene programas de pregrado. En un centro de investigación.
Sí, no, tu pregunta entendí que tenía que ver con que si previo a que los estudiantes fuesen a Francia, tendría que necesariamente existir una colaboración entre los investigadores, y la respuesta es no, porque tenemos estructurado el programa en particular de internships, la manera en que nosotros hacemos una llamada a tópicos de investigación al interior de Inria. Entonces son los investigadores en Inria primero que están interesados en recibir estudiantes, que por cierto cada año recibimos más tópicos porque el programa es súper bien evaluado. Entonces esa primera llamada nosotros recibimos los tópicos de investigación. Después nosotros tenemos acuerdo de momento con 3 universidades, pero hay una cuarta, que es la Universidad de Concepción, que se va a sumar, y por eso estamos ya en conversaciones con la vicerrectoría académica, y es la universidad quien selecciona a sus mejores 5 estudiantes, 3 estudiantes, los que decida que son, ¿vale? Entonces esos estudiantes, que son sus mejores estudiantes, que decide para participar de este programa, Inria Chile lo que hace es el matchmaking entre el interés, el currículo del estudiante versus los tópicos de investigación que hemos recibido ese año, ¿ya? Entonces, suele pasar también, hay algunos casos en que hay una colaboración preexistente, ¿ya? Pero no necesariamente eso es mandatorio desde un inicio, o sea, pero cuando eso sucede y esa colaboración es preexistente, efectivamente, y un profesor, por ejemplo, acá, o un investigador acá en Chile, tiene un estudiante que quiere enviar a un equipo de investigación y ese equipo de investigación en Inria envía un tópico, efectivamente nosotros, o sea, si queda seleccionado, pues le hacemos el match para que lo que haga sea alimentar la colaboración. Pero desde un inicio no necesariamente tenemos que partir por la colaboración entre los investigadores, y lo bueno es que este programa de internships promueve también la conexión entre investigadores en una temática diferente, es lo que te decía antes, entre los supervisores del mismo.
Entonces, ¿el estudiante postula de manera independiente a la universidad?
No.
A la Universidad de Concepción, digamos, para que la universidad seleccione a los 5 mejores.
Ahí sí, es la universidad quien hace entonces una llamada hacia adentro en las facultades de ingeniería, normalmente, matemática o ciencia o ingeniería matemática, no sé. Y entonces, normalmente porque es Digital Sciences, no hacemos de todo, ¿no? No va a ser probablemente a la facultad de astronomía, donde sea, pero es una cuestión a ver. Y en esa llamada es donde efectivamente los estudiantes postulan y es la universidad quien monta su comité de selección, ¿ya? Y decide quiénes son y nosotros no hacemos nada con esa selección de sus estudiantes, la universidad quien tiene toda autonomía, digamos, para hacerlo. Lo que hacemos nosotros, una vez que recibimos la voluntad de los hosts y de los investigadores en Francia de recibir estudiantes chilenos, es hacer ese match. Y eso es ahí donde está, digamos, el arte de que realmente sea efectivamente un programa exitoso, porque efectivamente, bueno, tenemos embajadores, digamos, estudiantes que han ido para allá, que después han terminado haciendo el doctorado, que vuelven y son profesores acá y que digamos, alimentan el programa en un círculo que es súper efectivo y que tiene muchísimas externalidades. ¿Más preguntas?
I would like to add something about the PhD mobility, because something came back to my mind. We described the internship program at the master level, but actually at the PhD level, you are building this PhD doctoral program in AI with 4 universities, and what could be possible through the frame of the associate team to have in the list of the people that will benefit from the associate team some of the PhD students from this new doctoral program in AI, and then through Inria Chile, we can vouch that artificial intelligence is a priority. So we can start from next year PhD mobility within the frame of associate team connect to AI. So we can add extra layer depending on what we want to build, because they are our homemade program. So.
In English or Spanish?
English would be nice, because then I will understand better.
Hello, I'm Rocio. I work in Matcom, a science-based company. We develop mathematical and physical models. What kind of collaborations and opportunities are in Inria for this type of companies or startups?
So
Can you tell me a little bit?
Yeah, I will definitely let Nayat answer, because this is one of the pillars of Inria Chile. It's also the connection with companies, so you can do it in Spanish.
¿Te respondo en español?
Vas-y.
Bueno, bueno, en Inria Chile también, bueno, igual que en Inria, o sea, además de tener un pilar de excelencia científica, tenemos un pilar de innovación, ¿ya? Entonces, digamos, nosotros no lo hacemos también aquí en Inria Chile. En Chile, digamos, tratamos también esos pilares más el pilar de apoyo a políticas públicas. Entonces, en el pilar de innovación hay algo que tiene que ver con la conexión con el sector privado y hay un punto especial que tiene que ver con el apoyo a startups de base científico-tecnológica, ¿ya? Deep Tech, ¿ok? Entonces, en ese punto hay, digamos, varios ejes y dentro de INRIA tenemos un programa que se llama Startup Studio y dentro de ese Startup Studio, digamos, en Chile, porque el Startup Studio en INRIA tiene otra manera de funcionar y otra metodología, pero en INRIA Chile tenemos también varios ejes. Uno es el eje de apoyo transversal a startups de base científico-tecnológica chilenas, que, bueno, necesiten, tengan algún desafío mayor en el que podamos nosotros conectar, ¿no? Segundo es que cuando estén en algún punto de ya crecimiento a nivel nacional, necesiten conectarse al internacional. Y lo que tenemos nosotros es un programa de internacionalización de startups de base científico-tecnológica chilenas, que las conectamos con el ecosistema europeo a través de Francia. ¿Ya? Y todos los años tenemos una llamada donde este año también recibimos algunas postulaciones también de por acá de Concepción. Bueno, aquí lo que te puedo ofrecer es que conversemos un poco más en detalle qué es efectivamente la problemática de la empresa en la que trabajas, de la startup, y vemos si podría entrar en este espacio de apoyo transversal o si estaría más ligada, digamos, al espacio más de internacionalización, y ahí podemos hacer las conexiones entonces con Europa. Normalmente en el eje de internacionalización necesitan tener ventas, tienen que demostrar ventas ya nacionales, porque está claro, si tú quieres aproximar un mercado adicional al tuyo, tienes que, bueno, ¿no? Entonces, como base, pedimos que tengan ventas nacionales, y ahí bajo el control de Julia, digamos, el resto de los requisitos, porque es algo que ocurre anual y que tenemos además muchísima demanda. Pero bueno, ahí lo que te puedo ofrecer es eso, que conversemos más en detalle, a ver cómo nos podemos conectar, ¿vale? Te conecto ya mismo con Julia, para que con ella. ¿Más preguntas? ¿No? Bueno, y esta caravana tiene ya que volver a casa. Esta caravana ya tiene que volver a casa después de 4 días intensos en la región metropolitana, un día en Valparaíso y hoy en Biobío. Ha sido para nosotros un esfuerzo tremendo, un desafío tremendo organizacional. Perdón, voy a dar las últimas palabras en español porque me han pasado todas las jornadas dando las palabras en inglés por los colegas después, y porque, bueno, esto se pretende que sea un encuentro franco-chileno, pero hemos intentado encontrar, digamos, un lenguaje que nos común. Por eso hemos tomado la decisión de hacer el resto del evento en inglés, pero efectivamente estamos en la casa también de la lengua española, así que voy a decir las últimas palabras en español. Entonces, bueno, eso, primero agradecer mucho. Les comentaba que ha sido un desafío enorme en términos de organización, pero ha sido, bueno, con muchísimo cariño que lo hemos hecho. Creemos que es así, que es como se tienden los puentes y el espacio. Lo que hemos querido hacer con esto es acercar la jornada científica hacia las regiones y hacia el centro del corazón de las universidades, que en el fondo son nuestros partners esenciales en Inria, ¿ya? Quiero agradecer nuevamente al Comité Científico de Concepción por todo el apoyo, y quiero agradecer al equipo de organización de Inria Chile, Enzo, Raúl, que no han dormido, a Julia, Paloma, a Luis, a Andrés, a Valentina, a Pamela, a Mifin, a todos que han hecho esto posible. De nuevo, ha sido un desafío tremendo. Espero que haya servido, digamos, el espacio para atender los puentes que queremos, porque la idea efectivamente es estrechar los lazos entre Francia y Chile en ciencias digitales, y ojalá que todo esto que hemos presentado hoy, que estas jornadas hayan servido no solo para mostrar, digamos, lo que hacemos desde Francia, sino para también tender esos puentes, y ojalá que se puedan aprovechar no solo a través de estos instrumentos, sino a través de mostrar más enlaces también y aprovechar otras muchas oportunidades que puedan estar por ahí. Así que doy por finalizadas las Jornadas Científicas Inria Chile 2023 y les espero a todos entonces en las Jornadas Científicas Inria Chile 2024.